Hey everybody, how are we doing? We're back live. Ashley, did you email me at B Stevens and did you email me this morning? Because I've been online this morning and I was just in a meeting. I was in two meetings. So you're literally just writing me an email. Was it this morning, Ashley? I've ever since about I guess like 10, I've been so probably if it was after 9 a.m. this morning, I haven't replied to all emails from this morning. It was, yeah, sorry. I was streaming and then I had a TA meeting and then I had another meeting related to someone doing research. So sorry about the delay in that, Ashley. I'll check the emails here in a moment. So I was streaming, then meeting, and now I'm back streaming again. So sorry about the delay in that, Ashley. You guys know I'd like to respond as quickly as possible, but sometimes, yes. Can you help with the very last question on the project? We got a question right here. Can we help with the very last question? You got it, Jackson. Let's do it. Let's talk about the very last question on the project. Turn the mic a little more towards me this way. So for the alternative hypothesis, do we say that it would be the true mean? It would be the true mean. It'd be mu. So it's always, since it's mu for the first one. I hope everything was all right with that. We'll take a look at Jackson's question here, and then we'll do as many questions as we can. So here we go. We're going to look at Jackson's question first. In the context of your research, what would a type 1 error be? That was a big error right there. So, and then we got a few more right here. Let's see. For Q3 Part D to enter uh, yes, you do enter. That is correct, right there, Sonny. You do put that in for the test mean. That is the value for the test mean. So, in context of engine life research, so we're going to drop some huge hints right here. We're basically going to write the null and alternative because I want to make sure everyone gets this right here. When you write your null and alternative, the null and the alternative for the test, I've done many different ways of doing this, so I'm just straight up dropping an answer right here. I did it this morning, so why not do it again here? Here is the null and the alternative for the test that we're running. So we're going to test to see if the true mean is greater than this value. Uh, I would, for part 4, I would just keep the decimals. Keep the decimals. That's always good. Should we give other possible variables we could have tested for? Yes. The biggest thing that I told, especially the graders, is that the intro says that you should talk about how statistics are important. So probably talk about that, and then you can go into additional ideas. But the importance of statistics in the outro and how we use data-driven decisions is very important. So probably go through a little bit of why are we making data-driven decisions? How do we make data-driven decisions? And then what could the company look for in the future? And why is it important to the company to make data-driven decisions? Don't just go through your report again. This is a huge thing if you're listening on this now. Your outro should not just be you going through, I did this, then I did this, then I did this, then I did this. That sounds like the executive summary. So your outro should not just be going through your whole report again because someone just read your whole report. So why would they read an outro of you going through the whole report again? So your executive summary is going to clearly outline the problem. It's going to give all the important facts and figures by numbers, and then it's going to tell Nissan what it should do. Did you hear those 3 key things? Your executive summary will, 1, outline the problem that Nissan is currently thinking about. 2, give every key fact and figure they found while doing this research. And then 3, make it very clear the decision they should make, whether upgrade or not upgrade, based on the data. And so we get into here, which is the type 1 error, which is the question that was asked earlier from Jackson. The type 1 error. Now, what is this? So someone's got to help me on the chat here. We got to practice. In a type 1 error, the null is what? What is this sign I'm making right here? In a type 1 error, the null is this. In a type 1 error, type 1, the null is this. So does anyone have any idea what the type 1 error, the null is what? In a type 1 error, the null is this. It's true. Great job in the chat right there. You guys are awesome. In a type 1 error, the null is true. Now, what are we going to do that's a mistake if the null is true? We are going to reject it. Now, that's not what you should do. This is why it's a type 1 error. So in a type 1 error, the null is true. So it is true. This is true. What I'm touching right here with my hands right now, this is true. But we're going to reject it and say we have evidence for this. Now, I don't want to say the full thing right here. Quick question, which video has chapter 17? Last Thursday's video has chapter 13. I did a little yesterday too. And look in the comments. You should see a lot of comments with timestamps. And then throw a like or throw a comment on the video too. If you find something in a video that helped you, put it in the comments and hit a like and like the other comments. More likes, more comments, help the channel a ton. Awesome, Carson. So in a type 1 error, this is true. So I don't want to give away the full answer for this. So I'm going to do an alternative problem right here below it. And I'm going to talk about a type 1 error for this. Let's say Brian goes to court, and the null is that Brian is innocent. And the alternative is that Brian is guilty. Classic examples right here. So in a type 1 error, I want you to just slow down here. Let's do it very precisely. In a type 1 error, the null is true. So what is the null, and what does it mean that it is true? So tell me in this instance, for the second example right here, what is the null, and what does it mean that the null is true? The null is this, and then what does it mean since the null is true? The null is this, and what does it mean since the null is true? The null is innocent, Brian is innocent, and it is true that Brian is innocent. But what are we going to do in a type 1 error? We're going to reject it. And we're going to say we have evidence that Brian is guilty, but the truth is Brian is innocent. Remember, in a type 1 error, the null is true. So we are going to, remember, careful, in a type 1 error, the null is true, but we reject it. In a type 2 error, there's the 2, the null is false, there's the F, and we fail to reject it. So in a type 1 error, the null is true, and we reject it. Now, without telling me any statistics, I want someone to explain to me what happens to Brian in a type 1 error. There you go. Nice job, Tiffany, right there. What happens in a type 1 error to Brian? I want you to look at this and say, this is true about Brian, but I'm going to reject that and say this. Brian's innocent, but we reject it and have evidence that he is guilty. Exactly, Sarah. Perfect answer right there. Brian goes to jail. And then make sure Barbara to answer. Great answer, Barbara, right there. Brian goes to jail when he's innocent. So remember, it's true that Brian is innocent, but we reject that and say we have evidence he's guilty. Now think about how that relates to this up here, that this is true, but we reject it. So think about what Nissan might do if this is actually true, but they reject it and they say have evidence of this. So what would they do if they think this is true, yet they reject it and say they have evidence of this right here? And Sophie is totally right there. You would go to jail even though you're innocent. And so in a type 2 error, talk about the type 2, which question really doesn't get into that. In a type 2, the null is false. So it is false that Brian is innocent. This is a false statement. Sorry, Brian. It's the beard. It is false that Brian is innocent, but I fail to reject this. So I continue to believe it. So someone explained to me in a type 2 error what happens to Brian. It is false that Brian is innocent, but I'm going to fail to reject this. Type 2, it is false that Brian is innocent, and I fail to reject it. So it is false that Brian is innocent. Yeah, we can do some chapter 17 in a moment. We did a lot of projects earlier today, so I might do a little bit of project here and then do chapter 17 because I know that's due tonight. So we'll put some priority on that. Great question, Austin, right there. We'll go back and do some chapter 17. What are we going over? Oh, we're just doing project right now, type 1, type 2 error. The last question on the project. And John, feel free to put your votes in for what you want. You don't go to jail and declared innocent even though you're actually guilty. Yes. You know what we're going to do? We're going to use Streamlabs to decide. We got 26 people watching. If you are watching right now, you can take part in the vote. Your vote will be for the project. So what should we work for the next hour, basically? What should we work? And so people are probably voting right now, but don't worry. So we've got project with a P, and we've got quizzes with a Q. Okay, so you'll see how the votes work in just a second. Let me bring up the poll for everybody. So we're starting the poll right here. Poll added, poll started. So make sure to vote via the commands in the chat. You're probably seeing people vote. So you'll have to do exclamation vote P or exclamation vote Q. I'm going to go with whatever it is. So it's just P or Q. So we're getting a lot of votes for projects. I will do some 17 near the end. I know, yeah, I did a lot of chapter 17 last videos. So if you guys are here, you get to vote. And then we can do conditions. I see Mackenzie wants conditions. It looks like projects is going to win. I like people telling their points. And then, so we got a lot of questions right here. We'll probably do conditions next. So we can always, I'll probably stream till like 4:30, who knows. We'll keep going as long as we got a bunch of people here working. Okay, so it looks like vote half-half. I should have added more options. Okay, so let me close the poll now. So, and there's probably a 3-second delay. And so the poll has been closed. It should say in the chat, it's definitely that the project won. So the project won right here, and it'll give the answers to which one won right here. It should show the, oh, complete. I closed it, but I didn't complete it. There we go. Poll is now complete. Still learning how to use Streamlabs. So there we go. Project one. We're going to stay on the project now. We may repoll later. Okay. On question 2C and 2D of the project, is the confidence interval the upper and lower of fail and safe? Yes, that is 100% correct right there, Elizabeth. We're just kind of doing rapid fire questions right now. When you make these confidence intervals, I'm using different data. You will put something in here like payment method, and you will get the following for different machines. Let me deselect this. So you will make your 95% confidence intervals. And these right here, I'll hover over them for you. Let me show only that. That'll be easier for people to see. But this, well, let's go to blank screen. Cool. And then let's take the data. Let's bring it over here. I will circle the confidence intervals. And of course, mine are very different. I'm using different data, but it's still just the same idea. And we go right here. And here are your confidence intervals you need. And then we'll mention the conditions for these. Your confidence intervals are the following. My confidence interval right here is I'm 95% confident the true proportion of people who use cash is contained in the interval 39 point or 0.3940. I usually use 4 decimals if I do it as a decimal. If I do it as a percent, I use 2, like 39.40. So carry it out enough that you're not missing the significant digits. Do we actually need to talk about the successes though? This one passes the success failure. Some of yours might not. To check success failure, which is the third condition for this, you need to look at this right here, which is the same as this right here. This right here is the success failure condition, either or of these. They're both the same information. But that is how you check the success failure condition. Does that make sense to everybody? That is how you check your success failure condition. 3D and 3E, I believe, are the statistical tests. So yes, Jay, great question right there, Jay. 3D and 3E are the statistical tests, if I'm not mistaken. Let me double check. I think I know which ones they are. This is why. Yep. And yes, you must include the statistical tests. Your output for 3D and 3E will look something like, let me bring it up. It'll look something like this right here is what you should be getting close to. It's not going to look just like this. I'll make it look close to it. It'll look something like that. Now I'm doing a totally different statistical test, but this is the way the output looks for 3D and 3E. Does that make sense? Did people get output that kind of looked? And once again, I would just screenshot this for 3D and 3E because this is all we need. So if I'm just doing a statistical test, I'm only going to screenshot that right there as my statistical test. Keep the questions coming. I saw there was a lot earlier. I saw some condition stuff, but that is, how do you know to reject or not reject based on that? Great question right there. And then conditions. Mackenzie, we got that. Make sure we're doing Mackenzie's next right here. I need to slow down talking. So here we go right here. Let's jump into here. And what do we have here? We have whether to reject or not reject. Now, we have to look at how we wrote our alternative hypothesis. So when we write our alternative hypothesis, it looks weird, right? Because you're like, wait a minute here. This p-value is what? What's going on with this p-value here? Can someone tell me, if I were to test, I'm going to write, this is not your question, remember, it's mine. So if I were to write here, the null is that the mean is equal to 7, because that's mu naught, and this is y bar. And I write here that the alternative is that the mean is greater than 7. Those are 7. I can make them look a little more clear. So can anybody identify for me what, there we go, like that 7. Can anyone identify for me what the p-value for this test is and what does it mean? This is where I think people have gotten massively confused on this problem. Can anyone identify the p-value and what it means? It's 1. Nice job, Julio, right there. Knocking it out of the park. P-value is 1. And so let's take a look at this right here. The p-value is 1 right here. How do I know that? It's this. We'll use the green pen, meaning it's a good answer. It's this connected to this. Now you might say, why isn't it this one right here? This alternative is for the what test. The one I've put a red arrow next to. The one I've put a red arrow next to is for the what test. I don't want to do it yet. The one I put a red arrow next to is for the what test. We failed to reject 100% right. Two-tailed does not equals test. Excellent work. That is the two-tailed does not equals. This is the greater than, and that's the less than in that order. Exactly. Great work, everybody. Excellent answers. So we use this test, which shades to the right. So, and then we got Mackenzie's and Julia's question. Excellent work, guys. So, and I think, Julia, that is correct right there. I'm 95% confident the true mean for engine life is contained in the interval blank to blank days. Yep. Excellent work right there. And so this is true mean because we're analyzing quantitative data. And you'll notice right here that my p-value is 1. Now, when the p-value is high, just let the null what? When the p-value is high, just let the null this. When the p-value is high, just let the null, let it be. Let it fly. You got it right there, Tiffany. Excellent work. When the p-value is high, just let that null fly. Just let it be. Don't do anything to it. You're like, what does let it fly mean? Let it be. I know it's when the p-value is high, fail to reject the null, but it works. When the p-value is low, reject the null. When the p-value is high, just let it fly. What does let it fly mean? Don't do anything to it. Now, that doesn't mean we believe it. It just means we don't have evidence to reject it. So we're going to fail to reject the null. We're not saying that this is true. We are saying that we don't have evidence of this. We did not find evidence. Does that make more sense to people? We did not find evidence that the mean tip amount for cash, this card, the mean tip amount for card was greater than 7. And this is a totally different problem. But I do not have evidence for the alternative because I do not reject the null. So let's write that in right here. I do not reject. And that means I do not have evidence. If you do reject, you do have evidence. If you do not reject, you do not have evidence. So are the confidence intervals for question 2 the true proportion is the true proportion? Yes, question 2 is true proportion, Julia. Great question right there. Yep. Julia, this one is quantitative. It's true mean. And question 2 is true proportion because it's categorical. So good questions right there. And I think we had Madison's question about conditions. So if it's in the black, then that's the one we should look at. Barbara, can you rephrase it? I don't understand the question 100%. If it's in the black, rephrase it. It's probably something related to what I said, and then I forgot what I said. So it's my fault. If you rephrase it, and I'll show you something about this output that I think confuses people. You can actually go here, and I was doing it earlier. You might be wondering why the p-value is 1 and you don't see anything shaded. It's because here's where we landed, and we'd shade to the right of it. So we landed right here, and 100% of the curve is above it. You can see this via the p-value animation, which you don't need to include, and we are doing the greater than test. So the greater than test would be to shade above where we landed. We landed all the way down here, so the low side is basically a p-value of 0. The two-tailed side is basically a p-value of 0. And above this line is basically the whole curve. Now, Jump doesn't think you'd want to test that because you don't have evidence for that, so it doesn't really show the shading on it. But if you notice, there's the line you see, there's that line, and then this is the probability greater than it. So it's just shading above it. Like one is in black and the other is in orange. Oh, no. Great question right there, Barbara. Amazing question. Million points, Barbara. Always look at the alternative based on the way you write your sign. If, for example, we had done a test where we had asked if it is not equal to, like, let's say my alternative was the following. Would I use p-value 1, 2, or 3? Which p-value would I use if my alternative is the does not equals alternative? P-value 1, 2, or 3? Because you always look at the sign of your alternative to know your p-value. So would I use the first, second, or third? Who knows for a million points in chat? Get some points today. Who knows? The trick is to always remember that these give away some of the answers. Because those p-value 1, yes, exactly right, because that's the does not equals. That's the absolute value does not equals alternative. Awesome stuff right there. I'm so proud of everybody. There's so many points. If you guys want to check your points, I saw some people doing that earlier. And let's keep asking project questions here. Mackenzie wanted the conditions, so let's bring back up the condition cheat sheet we wrote earlier. So it's somewhere in here. We did a condition cheat sheet earlier. Here we go. Okay. Condition 1. Who knows condition 1? Anyone know condition 1? Condition 1 is random, and wolves are cool. There we go. So condition 1 is random. So do we pass this condition for our project? We pass this condition because we've randomly selected our data. So if we randomly select our data, we pass the randomization condition. Condition 2 is 10%, which means we need less than 10% of our population sampled. So wolves are super cool. I like that right there. So in this project, we have a population, a big N right here, of 10,000 observations. And our sample size, little n right here, is something like 300 something. So 300, some sort of value right here. Just, we take 300 something. It's 300, some sort of value. Everyone will take different ones. So is your sample size of 300 something less than 10% of the total population of 10,000 engines we will be making a year? Is your sample size of 300 something? Definitely. Not that I'm giving away answers, but it's clear that we are taking less than 10% of the total population of engines that we would expect to make in a year's time. So we do meet that condition. We meet random because we had jump select a random thing. So we get into the next part here, but first we must remember pause, 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 stop, slow down. We have to ask ourselves, what kind of data are we dealing with? So I'm going to try to erase some of my my highlighting here so I can bring your attention. No, nearly normal y. There we go. Ah, got it. So here we are. We now need to ask, what kind of data are we dealing with? So we've got to look at the data, and if we have categorical data, it's success failure, which means we need at least 10 successes and at least 10 failures, which a graphic just like this, a guy like me, I miss Joker. So here we pass the success failure because this is categorical. Whether someone uses a card or cash is a categorical question. So this would be success failure. We need at least 10 successes and at least 10 failures. And you might say, well, these aren't successes and failures. They kind of are. It's from the project. It would be simple random sample because it had an equal opportunity of selecting everything. It'd be simple random sample. We could have stratified it. That would have been interesting because we could have said take 50 this, 50 this. Awesome, John. Excellent work. Great question. 1,000,000 points. So it is just a simple random sample because everything in the 600 you had access to had an equal opportunity of being sampled. And so now we see that we are checking the success failure. Why do we pass? We have 126 here and 106 here. We pass. If you fail the success failure condition, don't worry. Just mention it. Like, don't be like, it's no big deal. It is a little bit of a deal. It's something we shouldn't do. But sometimes we throw these curveballs in the project that we want you to notice. We don't want it to be perfect. Like, oh, you always pass these conditions. It's worth mentioning that, there's a failure on the statistics, so maybe there might be a problem with our analysis. So, but as long as you say you fail it, you're fine. We won't be like, how clearly did you? Just make sure it's clear that you failed it. If you failed it, it'll tell us that you know the condition. We're just trying to see if you can catch it. And some people will fail the condition from what I've seen. So that's success failure. Success failure is when you have one what type of variable. Success failure is when you look at your data and you have one what type of variable. It's when you're doing a one something z-test. One, and the C also means something, but it's due to the categorical, you're right, Barbara, and that'll be proportions. So it's a one proportion z-test. And so when you do a one proportion z-test, it's because you have one categorical variable, and excellent stuff right here. Now we get to when the data is quantitative. Now I want to point something out. I'm going to add an extra note on this. This is, in all instances, these are the y's. This is y, this is y, this is x, and this is y, and this is x. So proportions. Wouldn't machine and engine life require the nearly normal third condition? Yes, exactly. And which one of those is this? Is machine life and engine life only quantitative, or is it quantitative categorical? So which one is that right there? Whenever you have a chance for 4A, every time I try to do, you might have to email me on that, Christina. I'll look at that next. That's a really good question. And so Sani right here, which one? You mentioned machines and engine life. And here's the thing though, I will say this, let me give the answer. The way we are doing it right now is that you had the same problem, had to delete the last column. That's really interesting. I haven't seen that yet. You might want to send me a screenshot. It's kind of QC, and I'll say why we're not doing it that way. We are analyzing just each one individually. You could do it as a 2-sample t-test. You could do it as a 2-sample t-test and do the nearly normal. I've got the 1-sample t-test highlighted. It's going to, of course, scroll back up on me. But you could analyze it as a 2-sample t-test. This is a 1-sample t-test. This is a 2-sample t-test. What we're actually doing in this project is we're doing 2 1-sample t-tests. Does that make sense right here? We're doing 2 1-sample t-tests. We're not looking at the differences between the machines, but we're just breaking it apart and doing a t-test on the current machines and a t-test on the new machines. So we're doing 2 1-sample t-tests. Now, in truth, and I will say why we didn't do this, we could have done it as a 2-sample t-test, but the reason we often don't put that on the last project, glad that helped out Barbara right there. We don't want to put like the last few topics you learn. The project kind of goes up to like the second to last chapter, or the third to last chapter, because if we were to put the chi-squared on this, we'd be teaching the chi-squared yesterday, and you'd have the project due for extra credit today. So it's kind of been our theory that we shouldn't put the last few concepts, but you could do a 2-sample t-test on this. It wouldn't be bad statistics to do a 2-sample t-test. Awesome. Who said that? Tiffany, are you already maxed out on extra credit? Tiffany, you fixed a problem. You get maxed out. That is a huge help right there. Thank you so much. I think you just fixed the problem for Christina. And that's why I love having her in the chat, because sometimes there's a problem I haven't seen. Yep, you should do the nearly normal. You you guys are awesome in chat. And so you will only need the third condition right here. And so you're actually doing 2 1-sample t-tests. And so you'll use analyzed distribution. Can I use a nearly normal probability plot to prove the nearly normal condition? Or just show evidence of it. So let me go back to that for the nearly normal. We talked about this a lot earlier, and I've got some good graphics up for it. Where's that? Here it is. Here's my kind of talk on the nearly normal earlier, and I'll kind of give it again. So you notice I've got some things highlighted. So let's undo the highlighting. So much highlighting. There we go. So the first way to see if something is nearly normal is to just look at it. Does it look unimodal symmetric, or does it look skewed? Now, John was mentioning that he might try to use, which is not a bad idea, he might use a normal quantile plot. And did your normal quantile plot look pretty straight, or did it look pretty bent? Did it look pretty straight or pretty bent? Which did it look? If it looked straight, like the black dots right there are following it, that's good. If it looked very bent, that's bad. That means it's not normal. And this is good evidence. We would never say prove, but good evidence that the distribution is normal. So way number one. Well, here's the big thing, Barbara, and here's the big thing I want to make as clear as possible. My suggestion is, and here's we won't talk about the goodness fit, because I wouldn't suggest using that. People will get on a wrong route if they use that. This is what's going to confuse people, is I would suggest these 2 methods right here. These are your 2 methods right here. Because we're not interested if this distribution up here is normal. This distribution right here might be skewed. Now, if I were to do a confidence interval with this distribution and I take 25 observations, do you think this passes the nearly normal condition for making a confidence interval for the mean, yes or no? Rounding 2 decimals is not bad. They should be nice on rounding, don't worry. If it's a decimal like 20.28, that's fine. But if it's like 0.28, I'd probably round it to 4. Yep, 4C. We do 4C next. Talking about conditions. Awesome, Matt, Julia. With this right here, would this pass the nearly normal condition, yes or no? Be careful, because the trick here is you need to remember to look at way number 4. You need to look at way number 4 to know if it passes the nearly normal. Because this does not look unimodal and symmetric. So you'd say, nah, it doesn't pass the nearly normal condition. But does it actually pass? The answer is surprisingly yes. Because we're not interested in the distribution of single observations. We're interested in the distribution of the mean of sample size 25. So at this right here, we see all the single observations and we get a distribution of the mean. And what do we get when we do this repeatedly? A distribution that looks pretty normal. So all of a sudden now we have a normal looking distribution, which is the distributions of means of sample size 25. And so we go right here. Can anyone tell me what theorem this is? I'll max you out on extra credit for my class. Can anyone tell me what theorem this is that basically lets us use the distribution of the mean and say that it's normal? This is one way to check for the nearly normal, because if you have a large enough sample size, central limit theorem, Andrew, you're totally right. This is the central limit theorem, Tiffany, and both of you already maxed. You might be Elizabeth maxed out, Elizabeth too. We're good. Boom, we got it. So this is the central limit theorem stating that the distribution of the mean will be more normal and symmetric as we increase the sample size. So more normal and tighter, well, normal is symmetric, so more normal and tighter. And so this right here is the 4th way I've listed. If you look at the 4th way right here, it's the large enough n condition. So that's large enough n right here. And if it's unimodal symmetric, the sample size doesn't matter. If it's skewed, we need a sample size of at least 25. If it's heavily skewed, you need a sample size of 100. How large is your sample size? I would do the decimal, Tiffany. So to Tiffany's question, I would include the decimal. Decimal place accuracy just helps. I know it's a discrete number. Well, but think about this. If someone says it's going to last a half a day longer, that means something. Even like how old you are is not discrete. Like how many cats you own is discrete. You wouldn't say I own 1.5 cats. People will look at you weird. They always look at me weird. So we have right here, I would say those are not discrete, because days can be continuous variable. Discrete means that it has to be like 1, 2, 3, 4. So cats should be discrete, or cars you own. Yeah, no wonder. No, great. Like that's, I mean, that's, I like that you asked the questions. I'm like, yeah, it's like, that's what happens to me. I'm like, I had to think about it too, because I was like, well, days are like, how many days were there? But then you can be like, it's a half a day or something like that. So yeah, it's a really good question, Tiffany. Great job. And I think there was a question on, and thank you guys so much. I like the rapid fire. Hopefully it doesn't seem too ADD, but that's me. Whenever you have a chance for A, every time. Oh wait, we do that. We did this one, right? I think we did that one. Who has another one? Another project question. What do we have for another project question? Feel free to ask. The queue is open right now. It is your opportunity. Add party. Just do the rainbow. Oh no, there we go. Ooh, imagination. So 4C. Let's go to 4C right here. 4C. Okay. 4C. A confidence interval can perform a two-tailed test. Any value outside the interval is rejected at an alpha level of 1 minus the confidence interval. Are you able to reject 3,600 days that was tested in the previous problem? If so, at what alpha level are you able to reject it? So I made some output earlier. We still got that output up. So this is an output made, and I've kind of, like, big things. I always want to have big things ready that you guys can kind of see, like, okay, this is what my output should look like. One thing I want to make very clear is if you made your output look like this, I mean, I'd probably do that to it. I'd prefer you do that, because now you can actually read what this says. And in truth, I shouldn't have put a check mark on that earlier, probably. If I was a grader, so I'm revising what I said. I said, this is perfectly fine. I'd probably do -1. If I can't read what these things say and your table looks like this, that would not be a good way of presenting data. That is acceptable. So now that right there is acceptable. I just double clicked the boundary. So by double clicking the boundary between this, it'll auto size. Like if you have this kind of missized right here, you double click and it'll resize the boundary. I think it also expanded the decimal place accuracy. So it's kind of neat. That one auto changes the decimal place accuracy for me. This one right here is just a cleaned up version. You don't have to make it look like this, but nothing wrong with that. For 2C is the only thing we just say is I am blank percent confident. Yep. That sounds like it. Interpret your interval. Great job right there. For the confidence intervals, if it's true proportion, it'll be, the conditions will be Madison, random 10% and success failure. Random 10% and success failure. Where's our slide with that? Where's our, I think it's here. Where are you? Well, we just had it. There we go. So here's your cheat sheet for that, for the conditions. I didn't go over all of it. I went over it earlier and made this earlier. Sorry for my bad handwriting. Gosh, I wish I had good handwriting. And then, so we'll do Madison's. I see Katie's next right here. And so the question was, how do we know if the interval, I've got a thing on here for this one too right now. Here we go. Okay. So as everyone see in my Excel output, I have the following. I want someone to tell me, so we're doing the interval one, then we'll do Katie and Who Wants question next. So I want everyone to tell me what the interval here is if you create the interval. I want someone to solve for me the 95% confidence interval. Go ahead and solve for me the 95% confidence interval using this data. Who can tell me the 95% confidence interval using this data? Anybody? 30 to 33, exactly, 30 to 33. So I would say I am 95% confident the true mean age of people who came to the salon, and this is a totally different question because I'm analyzing age. I am 95% confident the true mean age of people who came to the salon is contained in the interval 30 to 33. So we go back here to our question right here, and we say, what if we were to test the value of 34? So we talked about this earlier, so let me change it back to a 95. If we were to talk about a value like 34, and we did a 95% confidence interval, that'd be the same as using an alpha of 0.05. Because if 95 is inside, 5% is outside. 95 inside, 5% outside. So with this right here, we can see that the confidence interval is analogous to the two-tailed test. Look at how this has the area on the inside up there, and then this has the area on the outside down here. Confidence intervals and tests do the same mechanical work. So 34 is outside the interval. You see the interval way over there on the side of the screen? 34 is outside that interval. So I want to know, do you reject 34? It's outside the interval. Or do you not reject it? Remember, it's outside the interval. You think the truth is probably somewhere between 30 to 33, and 34 is outside your interval. You reject it, exactly. So 34 would be in this like rejection region. If you were to plot the p-value, it'd be lower than 0.05. So I'm kind of showing what the p-value would look like, but it would definitely be less than 0.05, 5% alpha. This is kind of what we call a rejection region. Anything that would to land in here would have a p-value lower than 0.05. Like if you landed right here, your p-value would still be lower than 0.05. So a confidence interval can tell you whether or not you would reject a value. You only need to look at that value and see if it's contained in your confidence interval, do not reject, or if it's not in your confidence interval, do reject. Think about this. Dinner, let's go get steak. I'm gonna take Chelsea out for steak, and it's gonna cost between, they tell me, I call the restaurant ahead and they say, our steak dinners are $20 to $30. Our steak dinners are $20 to $30. So if someone said to me, do you think the steak dinner will cost $23? Do you think I'd believe that? Like if someone said, "Oh, I went there and it cost $23," would I believe their claim of $23 if the restaurant gives me an interval of 20 to 30? Would I reject that or not reject it? Hey, it was good to see you, Oliver. Would I reject 23 if they tell me 20 to $30? Would I reject it or not reject it? I might have switched up my question. Probably another hour. I would not reject it. I would not reject it. Not reject because it's contained in the interval. Think about that. You call the restaurant. They say steak costs $20 to $30 at our restaurant. Then your friend says, "Oh, I went there and it was $23," and you're like, "Oh, I believe that." But if they're like, "I went there and it cost $2," what would you say to your friend about them making a claim it cost $2? What would you say to that value? Your friend's like, "Oh, I went to that restaurant. It was $2 a steak." So the restaurant's giving you an interval 20 to 30, and your friend's like $2. If it's not in the interval, rejected. You got it right there, Julia. If it's not in the interval, reject at the 0.05 alpha level. And your friend who made the claim of $2, you would definitely reject that claim. If your friend claims $2, you'd be like, nah, I'm rejecting that. That's not inside my interval. That seems highly unlikely due to random chance. So the friend is crazy. I like it right there. You wouldn't believe him. What a steal. I mean, $2. I'd be afraid of a $2 steak. Like dollar store steak. I mean, nothing. Dollar stores are great a lot of times, but dollar store steak does it's words that don't go together. It's like dollar store plastic surgery. It's like I don't know about putting that together. That's not what you want. Like I mean, there's a guy on YouTube who like reviews dollar store stuff, and some of the dollar. I'm sure there's some good dollar store food. I mean, like Hot Pocket's not bad. It's about $1. So everyone's eating Hot Pockets now. So I think there's a question here. Let's go back to. We'll go on to another question. I think Katie has the next one, then Huon, and then Oliver's got some. I think. Hey Brian, when you get a chance, can you briefly go over 3A again? I know you went over yesterday, but I got confused because I think you did the opposite. Oh, I might have. I might have. Yeah, I think Katie, you're right. Katie, you're 100% right. You're saying I did the opposite on purpose. Good. I like it right there, Barbara. Um, so Katie is right. I did do the opposite yesterday. So if you're looking to confirm, Katie, I did do the opposite. Question 3A, if I am thinking about this correctly, asks you to make the distributions and then talk about the shapes. So to maybe today I'll do something more accurate to it. Well, this one's an opposite one again. Well, okay. So I'm going to do the opposite again today. So listen in here. So we're going to do the opposite again today. I think it's kind of clear because I was kind of hinting at yesterday, being like, hey, I'm doing the opposite. So your output for question 3A should look something like this. This is 3A because it has the shape of the distribution. And we go right here, we put it in here, and we have our output. Now this, once again, is not your output, but we need to talk about the shape, the center, and the spread. I want to hear a few really good words on shape, and we always start with shape because then it clues in us on the center. So the shape of this should be what? And I'm gonna draw a map on this. So this might help people a lot right here, remembering this concept. You guys are right, skewed right, unimodal with outliers, awesome stuff. Great work in the chat, Andrew and Barbara right there. So you need to go in the order of shape, center, and spread. So when you do this, if the shape is basically normal, green better. If the shape is normal, and normal looks like unimodal symmetric, then the center will be the mean. And the spread will be the standard deviation. If the shape is, giving some hints right here, if it's skewed, which basically means not normal, it could just be described as normal, not normal. Normal data gets the mean and standard deviation because then we can use z-scores on it. Then we're going to have median and IQR. Am I blocking it? Close, aren't I? Yep, right there. So in this one, would we use median and IQR for the center and spread? Or would we use, like the one I currently have on the screen, would it be median and IQR, or would it be the mean and standard deviation? What would we use for this one? Because we first need to do shape, then center and the spread. Median and IQR for this one, you are correct. Because this one is heavily skewed with outliers, and you could mention min and max. You don't have to do a ton on it, but you just definitely note that it's heavily skewed with outliers. Because of the skew, we're using median and IQR. The median represents that the 50th percentile of tips is $4, and the IQR represents the span of the middle 50% of tips is $3. But here's the thing, if it was normal, I would say something like, this distribution is normally distributed with an average tip of $4.97 and a deviation from that tip that is about 2.906 on average, or a standard deviation from the mean tip of this amount of $2.906. For question 3, should we show the histogram with... I would show them separately. I told the graders, I literally had the meeting with them, and I told them to be nice. So, as long as I was like, if they make a mistake, don't take up points immediately. Try to be nice. If you start to see things that look a little too much, like they're constantly putting things that you're like, I don't know about that, then start to take off points. So I told them to be as nice as possible. I would do graphics separately when you're talking about them individually, so I wouldn't put the test up here yet. So I wouldn't show it all immediately. I would show this, talk about this, and then I would do the test. So I try to like stagger my output. Because think about this, if you're the reader, if you get a whole bunch of output, then you're trying to read it and associate with what's going on. You want to immediately kind of see like, okay, here's the graphic, here's the explanation of it. So that's a really good interpretive thing right there to do, is to like show a graphic and then interpret it, not to show like 3 things and then interpret them all, because it can get a little bit confusing. That's why you often see like figure 1, figure 2, and then people can like go back to those images in like journals and stuff like that. There was another question, and keep asking those questions. I'll keep putting them in order. You can label them as long as it looks good. I told the graders to be nice, so they shouldn't be too mean. On 3B, it talks about 3,600 days, but in type 1 error, you talked about 3,600 days. So I'm confused what 3B is actually asking for. Cool, let's look at 3B and let's double check. Thank you there, Coolants. Coolants Questionnaire. We got 3C. We'll do 3C next. Yep, Sydney, you are right. You need to talk about shape, center, spread in 3A. That is correct right there, Sydney. So we go back here. Question 3. Make sure... Wait. Yeah, that's right? Was it not 3A? Let me double check. Include a graphic, interpret the distribution. Yes, right here. There it is. There it is. It is there. It doesn't say talk about shape, center, spread, but interpret the distribution for the new and the current machines. So I think a lot of people will miss that. That's why it's in bold right there, is because you have to interpret the distributions and talk about the shape, center, spread. So that's what it means to interpret the distribution. Connor, good to see you here. So, and so I think other people are asking, they'll have us here. Yep, Tiffany, you are right. Tiffany and Sonny, thank you for helping each other out. Excellent work. Yeah, I just want to make sure. Yep, awesome. And so for 2B, the company is interested to write and perform a statistical test. There are 3 conditions. So the question was about 3B. I'm trying to remember what the 3B question was. 3B is only doing the conditions. So 3B right here is your conditions. 3B is the 3 conditions. So what's condition 1? I need to know condition 1 for 3B. What is condition 1? Condition 1, I need to see in the chat. I'll help you guys out here. There we go. Condition 1, satisfying. Condition 1 is random. Condition 2 is 10%. Condition 3 is nearly normal. And we went over that earlier, so double check or rewind the video. And I did a full explanation of it earlier today, but I will, if a lot of people ask, I will redo it because you guys are here live, so you guys always get to vote on what we do. For 3C, it's just writing out the null and the alternative. So 3C is to write the full null. Oh, Abigail, amazing work. Abigail, have we maxed you on extra credit? Abigail, you're maxed out. You remembered better than I did that I always say pause because you have to ask what kind of data it is. I should label all these, but I just make more and more. But we have here pause, and then we figure out what kind of data it is. We have here the 1 proportion. The highlighter, you can look at the top of the screen. The highlighter is on. Nope, apparently not. Now we got the highlighter. The 1 proportion z-test, the 1 sample t-test, the 2 sample t-test, and the chi-squared test of independence. You're welcome, Abigail. You're doing excellent. I appreciate it. I like it when you guys say things that I even forget to say. There is a 4th condition if you are doing the 2 sample t-test and there's a fourth condition if you're doing the chi-squared test of independence. So you can see here the fourth conditions for the two-sample t-test is that the two means are independent, and the fourth condition for the chi-squared test of independence is that the expected cell counts are greater than 5. So good review right here. These are all the conditions for the test. Every single condition that could be on this test is right here. You've got one proportion z-test, one sample t-test, two sample t-test, and chi-squared test of independence right there. Of these three are the ones you're asking. Yeah, you got it. Awesome. Great job, Huan. So you guys are awesome. Next question. I think I saw another one. So let's look at that next question. Okay, I think we got Tiffany's question. So who's got another question right now? You said in the first question of the project that we should use the random sample 300 for the remainder of the project. Are we using the sample or the sample plus the UTID? Sorry about that. Hopefully I didn't misstate it. Yeah, it should be like the 300 something sample. Use 300 plus the last two of your UTID. Yeah, sorry. Sorry. Oof, that's Oliver. We're maxing you out too. That's an amazing note to take right there. Sorry about that. Of 300 something. That's a good way of writing something. But this sample size of 300 something, whatever you got. So Oliver, amazing note. I hope no one makes that mistake. You should use the sample size of 300 plus the last two of your UTID. What is the best way to avoid a type 2 error? Cool, John, let's talk about that here. Could I use the normal quantile plot for nearly normal? We talked about, I'll go back to the moment again, Lindsay. I would suggest, and then we'll do John's question right there, and then Oliver's on, let's do it. I would suggest these two ways right here. Rewind the video if you want, Lindsay, check it out and ask again in a moment here, and I'll come back to it. But I would suggest these two methods right here. A normal quantile plot is not the worst, but that is checking the parent distribution, not the distribution of the mean, which is what I talked about earlier, because we're not interested if the parent distribution is normal. We'll probably do it by way of large enough sample size, large enough n. So what Tiffany's pointing out right here is by way of large enough n, even if it's not normal, our parent population, and then Tiffany's also pointing out that right there. Yep, Tiffany, you are correct. And so let's answer that one right here. We'll do a little lesson for John right here. Great question, John. There are three things that will impact type 2 error. These are notes you should take right here. If you're watching, you should know there are three things that impact type 2 error. The three things that impact type 2 error are sample size, alpha, and effect size. So if any of these go up, type 2 error, which is beta, will go down. Now, we also should know that power is 1 minus beta. So 1 minus, I don't know how to write a 1, apparently. 1 minus beta is power. So when you look at this right here, I want us to remember what a type 2 error is. A type 2 error is going to be, let's go, my friend Dexter Morgan is on trial. My friend Dexter Morgan is on trial. Who knows what for? I don't know. He won't tell me. Dexter won't tell me what he's on trial for, but the null is that he is innocent. No spoilers. I'm not caught up yet. I'm way behind. Just finished season 2. So whatever you do, don't put spoilers in the chat. No spoilers in the chat. Whatever you do, don't scare me, chat. I'm too afraid to look at chat now. But yes, watching Dexter. That's my quarantine show right now. But Dexter Morgan is on trial. So what do you think? I know it is. I know season 2 just blew my mind. No, make sure no spoilers for jaywalking. That's what they got him for. Whatever you do, no spoilers in chat. Thank you, everybody. Yeah, you guys are doing awesome right now. Okay. I like pause and like, should I say it? And then I'm like, uh-oh. Okay. So what we have right here is, let's think about how this relates to his court case. If they were to call in no witnesses, do you think they'd be more likely to make a type 1 or type 2 error? They call in no witnesses. Do you think they'd be more likely to make a type 1 or type 2 error? You have to think what a type 1 and type 2 error are. If they call in no witnesses, and what is Brian changing? He's made the what here very small. He's made the what here very small. I've asked 2 questions. I should never do that. They call in no witnesses. I've made my sample size very small. They'd be more likely to find him what? Type 2. You are right. Because Dexter is guilty. So they're going to fail to reject the false null. In a type 2, the null is false. Dexter is not innocent. Sorry, Dexter. In a type 2, the null is false, but we fail to reject it. Does that make sense? In a type 2, the null is false, and we fail to reject it. So it is false that Dexter is innocent. He's actually guilty, but I fail to reject that. So beta is actually the probability of a type 2 error right here. The way to remember this, that beta is the type 2 error, great question, Oliver, is we say 1, 2, A, B, plus, minus. This is another kind of note segment right here for us, is that we remember that a type 1 error is associated with alpha, and it's a false positive. Type 2 error is beta, and there you go right there. The B is beta. Nice job right there, Tiffany. Excellent work helping each other out. But we have here that if you increase your type 1 error, which this is, oops, this right here is your type 1 error rate. So I guess maybe I'll put more time. I'll put alpha, and that's a type 1 error rate. And this is beta, and beta is a type 2 error rate. So your amount of type 2 error is your beta, and your type 1 error is your alpha. Alpha and beta are inversely related, but they're not complements of each other. But here's what the question says. It says you cannot change alpha. It says alpha, which you can change, but the question says you can't. Alpha is the percent of time we make a type 1 error. That'll impact how much we make a type 2 error. Think about this. You could make a type 1 error, like now Brian's on trial. Brian's on trial for all the things Dexter did. Oh, gosh. So Brian's on trial for all the things Dexter did. And what would be a type 1 error in Brian's case? A type 1 error would be what with Brian on trial for Dexter? For what Dexter did. They don't know that, but I'm on trial for what Dexter did. So what would be a type 1 error? And remember, in a type 1, the null is this. The null is true. This is a T for true. Then type 1, one's one right here. The null is true, and we reject the null. So the null is actually true. So what happens to Brian when they make a type 1 error on Brian? So Dexter goes on trial. They make a type 2 error. So Dexter, the null is false. He's actually guilty, but they fail to reject it and say he's innocent. But in a type 1, the null is true. Brian is actually innocent, but they reject it and they say Brian is guilty. So remembering examples like this hopefully will help you when you have to say, like, the null is true. It is true that Brian is innocent. Great job right there, Connor. And I reject it and I say that Brian is guilty. We always want to remember these kinds of examples right here that'll help us out in doing it. So we can't change alpha. That's what the problem says. Now you might say, well, why can't I change the effect size? The effect size is the true difference between the null and the truth, or the difference between the null and the truth. So it would be this one. Let me see if I can try to figure out how it would work in this one, the effect size. It would be like how guilty I seem. Now, the truth is that I'm not guilty of the crime. And then, well, no, the null and the truth. So the null hypothesis, yes. And then the truth would be how guilty I seem. That is correct. And then the null is that I'm guilty of the crime. So in this example, where would it be easier to not make a type 2 error? It'd be easier to not make a type 2 error if Brian was out he was in all these towns where all the crimes happened, or Brian can prove he was under quarantine. And we'll do quiz help after this, I think, Carson, because we've done a lot of projects today. It's awesome stuff. We'll do quiz help, Carson. I know you're here for that. See if people want to switch over to quiz questions. Which of those would be easier to not make a type 2 error on? Which of those would we be less likely to make a mistake on? Because remember, if we increase effect size, we would lower the type 2 error rate. Awesome, Carson. And the answer is, because I might have tricked you, I'll repeat it. Which of these would be easier to not make a mistake on? If Brian was in all the cities the crimes happened in, like when they happened, or if Brian was here at home under quarantine? And the answer would be, it'd be easier to not make a mistake if Brian was home under quarantine. Because what the truth is Brian was home under quarantine, and what the null is Brian is innocent. So let me see if this all works out. It's such a weird example right now for this one. And we would have no evidence for it. And the difference between the null and the truth, we would not be able to reject the null. We would have a very powerful test right here because we're so far away. And the last part of question 4, cool, Daniel, we can do that next. I'll do my favorite example for this one real quick because I think it makes a lot more sense. Let's do one more example because I like effect size a lot better. I really had trouble doing the Dexter example with effect size. Let me do the effect size this way. I like doing this example. It's one awesome, Tiffany. I'm glad it makes sense because even I was like, I hope I'm making sense. No one was replying, and that's why it always scares me. We have here the mean of how far Brian can throw a football, and the mean of how far Tom Brady can throw a football. So we got Tom Brady right here. We need Zach in the chat. Then we've got the mean of how far Brian can throw a football and the mean of how far his brother Darren can throw a football. And here's the null hypothesis for each of these. So these are two different null hypotheses. So I want you to tell me which of these would it be easier to reject the null for? And I think I know, hopefully a statistician didn't watch Alapar. I think I see what happened with my example. So can anyone tell me which of these would it be easier to reject the null for? That Brian and Tom Brady have no difference, or Brian and Darren have no difference in how far they can throw a football? Which of these would it be easier to reject the null for? And what you're actually noticing is the effect size. Which of those would it be easier to reject the null for? Brian versus Tom Brady, or Brian versus Darren? You and Tom Brady. And does everyone see that Tom Brady is just going to throw it like super far downfield? Now, Darren's going to do a great job too. It's going to be easier to reject the null that there's a difference between Brian and Tom Brady than Brian and Darren. Even though Darren's better than me, obviously, it's going to be harder to reject the null because there's less of an effect size. But what could you do to maybe see if Darren is truly better than Brian? Even though Darren is better, he's not as much better as Tom Brady. What could you do, like when you're testing Brian and Darren, to see that Darren is better, to be able to reject the null, not make a type 2 error? You could increase your what, and we've basically given the answer away again. You could increase your what to see that Darren is better than Brian. You could have us go out there and throw footballs and do what to the, do you see what I'm saying? Don't just do it one time. Multiple throws, you got it. That would be an increase in the sample size. Nice job, Lindsay, right there. You could have us do multiple throws, because if we only threw it one time, that'd be a very small sample size, and you might make the mistake of saying there is no difference. Because think, if Darren and I throw a football one time, you're like, Darren threw it 40 yards and Brian threw it 35. That's not much of a difference. But maybe that was one of Darren's bad throws and that was one of my good throws. Like I was like 35. Wow, I threw it. I don't know if I could throw a football 35 yards. I don't know what is good. Probably like 20 yards is good for like normal people. Like NFL probably is like 35. They can throw like 60 or something crazy. Would a type 1 error be like saying the current engines last longer? So we're only comparing it. Remember, our null hypothesis is we're looking for evidence that the engine lives are longer. So we're looking for evidence of this right here. We're just doing tests on the engines to see if the engine life for either machine is above a certain amount. So we're not technically on a 2-sample T, which we're not doing on this project. But Jeff, I think you are correct. On a 2-sample T, it would be saying that there's evidence of a difference or that one lasts longer because you reject the null. In a type 1, the null is true and you reject the null. And so the 2-sample T, which Jeff kind of alluded to, would be, if we wrote out, this is not the answer. This is not the answer to the project. But the 2-sample T, I got to slow down writing. The 2-sample T would be that mean for current minus mean for new is equal to 0. And then the alternative would be that mean for current minus mean for new is not equal to 0. So the 2-sample T, we would have evidence that there is a difference between the machines when there's not, but then look back at the problem we're dealing with and think about how our problem relates. How does our problem relate? What would we do in a type 1 error? Because this is true for us right here, but we're going to reject it and say this. Does that make sense? I don't want to say the answer 100%, but who here thinks they get my drift that in a type 1 error, the null is true, but we're going to reject it even though it's true. We're going to make the mistake and think this is true. That should basically leave it away. And think about what the company will then decide to do if they have evidence for one of the things that they are trying to look for. Does that make sense? I think we're going to reject the true null. The null is true. You got it? Awesome. So in a type 1 error, we reject the true null. In a type 1 error, the null is true, and we reject it. So I think you are getting it. Awesome. And this is the null alternative you'll be using for the project. Carson, which question did you have, Carson? Let's hop in and do a My Pearson question. Carson, you get to pick the My Pearson question. Which My Pearson question do you want to do, Carson? Which My Pearson question should it be? We will see. If anyone has a My Pearson question, let's do that. I'm pulling out My Pearson as we speak. Course tools. Okay, which one is it? Let's see here. Could you do chapter 17 quiz with the trips to the stores? Yeah. Can you do question 4 on chapter 17 homework? I think Joel got it first right there. This is kind of an off the wall question, but do you feel like the pass fail grading is um so yeah, I can answer that. I can give once again, please talk to all advisors. My view on this, Braden, right there, is second to anything an advisor will tell you. One, this is crazy, crazy times. Everything's absolutely nuts right now. So one thing we've talked about with all the stats teachers is that we are going to be as nice as possible. Like that's why we're averaging your quizzes together. Um, I would say unless you're I think all teachers across UT are gonna. I can't speak for all teachers, but I've heard a common sentiment among educators that we're trying to work with everybody about every unique situation, and we're trying to, told me that it shouldn't be detrimental, but it depends on the college if we transfer to grad school. Yeah, that's take their advice over mine. Like, if they encourage you to do something, I'd go with the advisor. That's what they get paid to do, and I'm just here as a person who experiences these things and can tell you what I think. But their advice is paramount to mine. But I can at least talk about our stats classes and say that being that I'm the statistics 201 coordinator, and Terry will be the new one. So congrats to Terry. And I've been it for I've been it for 4 or 5 years now. I think 4 years maybe. I don't know. It's been a while. I grew a beard. I was clean shaven day one. Um, aw, well, you're welcome. No, my biggest life tip is just always have goals. Always be working towards things. Your class is the important one for me this semester, so oh, that's awesome. Well, thank you, Andrew. Um, we are going to be as nice as possible with grading. I mean, we're not going to give someone an A if they don't deserve it, but the rounding is going to seriously go in your favor. We're going to make sure the average on the final, because we are doing another electronic final, is very fair to everybody. We're not going to put a final out that has an average of like a 60, 65. The average is going to be comparable to all previous semesters because, we're just in this weird situation right now where education might take a backseat to people caring for relatives, worrying about things, any sort of depression or anything that might hit being at home all day or things like that. So we are being very understanding with how the grades are, considering this has been a very interesting semester. And so obviously people are not going to get an A just at random, but we're going to go more in favor of the student than we've ever gone before. Not saying we're ever mean to students before, but we're doing as many benefits of the doubt as we can do. Does that make sense to everybody? So oh, John, that's so cool. John, why are you not a mod on the channel? Yeah, I'll totally still be here. And so I'll still be here completely. I'll be streaming. I should, as long as travel's safe, I'll probably come back to UT. Who knows, I might do it in my car. Thank you, Carson. You're awesome too, man. You guys you guys make me so happy. So, I I guess I'll say it. I just found out. Well, no, I'll say later. There's the thing. I haven't told someone yet, so I need to tell them first. I want to tell them first. So yeah. Well, you guys are really awesome. You guys make me so proud. Yeah, we do the positivity in here. Um, yeah, no, thank you. I'm glad you guys like this. Please, I'll probably send out a thing about whatchamacallit. The survey is due Monday. My hair's just getting crazy long. It keeps going into my face right here and blocking my eyesight. And then I think Oliver has a question too, so we'll hop back to this right here. But thank you guys for the motivation right there. You guys give me a lot of strength to do all this and keep me energized. And that and the orange juice. You say in question 2 that you have to describe the conditions met for a conference. How do you describe the nearly normal condition? Rewind the tape, Oliver. Check it out, and I'll maybe come back to that. You'll see, if you see the following graphic in the video, it's also in the morning video. This graphic right here, if you check out the morning video, it's in there too. Orange juice is the best. Pulp orange juice. Gotta love it. You'll see me talking about this right here, Oliver. Check it out. And if you're still stuck, I promise we'll do it again. You got it. Do you want us to send confirmation? Oh, you don't send confirmation. I'll talk to the other Stat 1 instructors. And then in question 4, I think, okay, we're gonna hop back on topic here. You ready? I think, Daniel, you're talking about the project. We've done question 4, and there won't be, these are not the 4 conditions right here. Check back, Oliver. This is how we can check the nearly normal. And that's earlier in the video, Daniel. Check it out. And we're going to hop back on. You have an outlier in your graphic for 3A and confused on what it represents. It would be an engine that is far away from the others. It would be something that was unusual, and it would just be one observation that's unusual. Probably worth mentioning that when you describe the distribution right there, we're going to do a little bit. I promise we'll come back. We'll do more project. We're going to do a little bit of chapter 17. I think people want it because we did check the video back, see if you can find the parts, especially if you see me talking about this and how to do the conditions. And question 4 was done earlier, but I will come back to it. We're going to go at least for another hour. So check back and let's see the questions. You guys are just so nice to me. All right, can you do chapter 19, homework problem 4? Okay. Chapter 19, homework problem 4. Chapter 19, homework problem 4. Here we go. We will come back and do some more project. We're going to do a little My Pearson for now. Okay, how's everybody doing? We got this back up here. Chapter 19, homework problem 4. And thank you for everybody. So everybody who puts comments in the videos, you're welcome, Elizabeth. Comments, if you like the video, if you comment on the video, if you subscribe, you really help out the channel. We appreciate it. And then after that, put the one you have again, Carson, in the chat. We'll do that right after. Let's do this. Okay, so something I want to point out right here is that chapter 19, there's a really great thing you can do with chapter 19. Chapter 19, if you have, does anyone have a TI calculator? Does anybody have a TI calculator? Any single person, one person have a TI calculator. So if you have a TI calculator, you can do the chi-squared test of independence in a TI calculator. So let's go ahead and grab this video link right here. So we're going to stop the video and let's go back. And awesome. So everything I'm about to do can be done in the TI calculator. Make sure I sent the right link right here. So the TI calculator, this is a video I made. It's a very, very short video on it. It's only 2 minutes. And you can do everything I'm about to do in the TI calculator. Now, the harder time showing the TI calculator version of this, because it is, I have an emulator I probably can use on YouTube. I don't have it on this computer installed yet. So everything I'm about to do, you can do in the TI calculator or with Jump. I'd probably suggest the TI calculator. Now, do we do the chi-squared test of homogeneity or do we do the chi-squared test of independence? Does anyone know, is it the chi-squared test of homogeneity or independence? Like when we taught the lecture, did I say the chi-squared test of homogeneity or independence? Because think about the null and the alternative. So we do the chi-squared test of, who knows? Independence. Nice job right there, Abigail. You are right. It's the chi-squared test of independence. Now, don't read their answers. This is how you get really great. Yes, I like that right there, Sonny. You're right. If you use the TI calculator and you know how to use it, it can make it really quick. I should do like TI calculator help sessions. If I can use the emulator on YouTube, which I probably can, I should do that. And I need to get the emulator on this computer. I don't have it yet. I don't know if I can find it again. So here we are. What is our trick for knowing the null and alternative? All we put is one word between this. For the null and alternative, all we do is go right here and go independent. That's all we do. Now, don't just, you're not done yet. You actually have to read it. You have to say that somebody's gender is independent of political party and somebody's gender is not independent of political party. So all you do to do the chi-squared test of independence, null and alternative, is you say that somebody's gender is independent of political party is the null, and somebody's gender is not independent of political party is the alternative. So there we go, and not is the alternative. You're exactly right. Now, they might have switched up the way the X and the Y goes. It can go that way. So political party is not independent of gender. We need to choose this one. Political party is independent of gender. Political party is not independent of gender. Nice job right there. Great job on the points. We got that one. Here's where people get stuck. Well, here's our conditions. Once again, we can go to our condition graph. I think it's this one right here. So condition 1 is random. Well, we'd hope that these individuals were randomly selected. Condition 2 is 10%, which means we've selected less than 10% of all males and females. Condition 3, pause before you do it. Please pause. We're using categorical data. Now, it's categorical data because both variables, or it's count data because both variables are categorical. Gender and political party are both categorical, so we pass count data. Literally by it being categorical, you pass. So it's kind of a redundant condition because it's like, do we pass count data? Well, yeah, because we're doing the chi-squared test of independence. So how do you know you can do it? It's because it's count data. The expected cell count, I don't know if it'll have us check that. I can check that, but we need to see that there's at least 5 expected cell counts for each group. So let's go back here. Those are all the conditions. Is count data met? Yeah, because it's 2 categorical variables. That's why it's met. 2 categorical variables is what it means. Is the randomization met? I wish they said it was randomly collected. And please watch out. They will switch the order of yes and no. That's tricked me before. I would think would be the first. Oh, they just did it. It's definitely caught me before. Is expected cell count met? Now, here's where I want to slow us down a little bit. A lot of people just put yes here because the answer is yes. But why is it yes? Can anyone tell me? I think it will be that one. Well, that's a bummer. We have to go through, and I'm adding them up in my head. Hopefully I'm not making a mistake. It's 92, right? Yep, I think so. Good. And 132, 210. I'm going to double check my work here. And then this would be 11, 17, 117. And then this would be 93. That should be 93. So that's 40, that's 93. Cool. Okay, I think oh, you can't see it. I think I've done everything properly right here. How do I check the expected cell count condition? How do I check the expected cell count condition for this? All the expected cell counts need to be greater than or equal to 5. The formula for expected cell count is row total times column total over grand total equals expected cell count. That is the formula. What do we mean by row total? This is a row total. This is a column total. This is always the grand total. Can anyone tell me what this formula just found? This formula right here that I wrote, 92 times 117 over 210, found the expected cell count for which one of these? This found the expected cell count for which one of these? I just found the expected cell count for what? Who knows? Someone's got to tell me. I've lost my memory. This is the expected cell count for which group? Who knows? To figure out which ones it's the expected cell count for, I still need you to tell me in the chat. Pause the video if you're trying to figure it out. You have to zero in on it. You have to go this way. You're welcome, John. So glad to help out. You have to do this. And then do this. It's for male Democrat. Does that make sense? It's for male Democrat. That's where the two lines would cross. Sometimes I'll do it just really quicker and I'll go, and you'll notice it crosses right there. That is the expected for male Democrat. Does everyone see? Because that's the row total for male and the column total for Democrat. So that's the amount of male Democrats we would expect. So when you're working this, you actually have to do it all. You'd have to do every single one of these. Does that make sense right there? Tell me what formula this is. This formula right here is the formula for what? That formula, 40 times 93 over 210, is the expected count for what? That is the expected cell count for what's. So you have to cross in on it. You have to do this. You have to make sure they cross. That is the expected cell count for which group? It's the row total for this and the column total for this, so it has to be the expected female independence. You got it. Nice job, Abigail. Practiced it up. Got it down. I like that. No, it is, right? Female independence? No, just female independence. It's expected, and so remember, always cross in, go like this, and go like this, and you notice that's where it hits in the middle. So it'll be for both groups. It's how much you expect for female independence. Does that make sense there, Tiffany? Independent females, you got it. If you notice, this would be the smallest because these are the two smallest numbers right here. So we have to solve this and see. Great job, Tiffany. And we have to see if this is greater than or equal to 5. So the answer is going to be yes, but still. So it's 17.7. And that's how many females we would expect. No, you did quite fine. Great job. So is this greater than or equal to 5? It passes that we have at least 5 right there. So we go here. We say it's met. We don't get tricked by them. And then it wants the chi-squared test. Now, this would be a lot of work. You would have to solve all the expecteds, all the cell chi-squareds, and then you would add up all the cell chi-squareds. Step 1, have your observes. Step 2, get your expecteds, which I just got one of them. Then do observed minus expected squared. Let's go back to our sheet. You would literally take all of these expecteds, and it was like you would do for this one, the cell chi-squared for this would be like observed minus expected. I knew I was behind my head again. It's observed minus expected squared over expected. So that is equal to 12 minus 17.7, I think it was, squared. No. Over expected. And that'll just get you one cell chi-squared. Please review yesterday's lecture. That is just one cell chi-squared. I don't have time for that. I don't have time to solve all the cell chi-squareds. So here's what I'm going to do. I'm going to take this data, I'm going to put it into Jump. So here's where life gets easier. If you put it in the calculator, life gets easier too. You go here, copy to clipboard, you copy your data. So slow down the video, pause it right here, make sure you copy your data. Once we've copied the data, we're going to go to Jump, and we're going to go to File, File, New Data Table. You can do that anywhere within Jump. You just go to File, New Data Table. So now that we have a new data table up, do not click inside of it. That's like the number one mistake I see people make right here. They just click inside of here. Don't do that. Don't do anything. And so we go right here and we go to Edit, Paste with Column Names. And so now we've got it in here. So you'll notice that this is red, this is blue, this is blue, this is blue. Don't continue if you've messed this up. If it doesn't look like this, redo a new data sheet and paste with column names. I'm doing the quick commands to do it right now, but if you rewind the tape, you'll see me do it, and I did edit, paste with column names in a new sheet. I'm pretty sure, because I see people do this a lot, I'll see an error like this. They'll click inside of here, and then they'll paste, and that's wrong. That is completely wrong. And then I see people, let me try this. They click inside. Yeah, now it won't paste. So do not click inside of there. It's a very common mistake. So now that we're here and you've confirmed, and rewind the tape if you don't see where I got this from, but also you can do it on the TI calculator with the link I posted in the chat. So have you done the type 1 error question yet? Yes. The type 1 error, you will see a graphic. You will see the following page in the video right here. It's at the very, very start. Very, very start. Go to the very, very start of the video, Ashley. I do it in the first 5 minutes, I'd say, Ashley. Great job. Good question, Ashley. First 5 minutes of this video is the type 1. You'll see this screen right here. And if you see me talking over this screen, I'm doing the type 1 error. So, yep. You're welcome, Ashley. Glad to help out. I really like that this is all live and you guys can, like, do that. Yep, and then, Carson, you got it. Carson, thank you, Carson, for waiting. I know you've been here quite a while. We got you next, Carson. We're going to go here to Tables and Stack. This is the next step right here. We're going to double-click all this right here and put inside of here with Stack. You bet. And let's go ahead and click OK. And here's what you need to get to. So now we have our data this following way. And so we have the data and we have the labels. We're going to go here and go to Analyze Fit Y by X. Now, the common mistake I see people make is they do not put the data in the frequency. Common mistake is not putting the data in the frequency right here. Just so you can see, you must put all of these here. Your two red ones go there, and then your data goes there. You click OK, and you have the answer. The chi-squared is the chi-squared Pearson, the Pearson chi-squared. It's 12.151. And we'll go back here. We put in our chi-squared of 12.151. We check our answer. It likes it. The p-value is going to be very small. I bet it's that one, is it not? Oh, it is. I got it right. Yes. Can anyone tell me the degrees of freedom on this test? Who knows the degrees of freedom for this test? It's a 2 by 3. 2 by 3. The degrees of freedom are what? 2 by 3. The degrees of freedom are what? Who knows the degrees of freedom? It's a good check to see if you know it like that. Since it's a 2 by 3, 2 by 3, reduce it down by 1 each time. And right here. And then we can do that. Annalie, we can do that one next. You got it. So I think Joel and Carson have some questions. And so the p-value is low. Everyone's right. It's 2 degrees of freedom because it's a 2 by 3. You reduce each finger down by 1, and you times 1 times 2, and you get 2 degrees of freedom. So it's rows minus 1 times columns minus 1. 2 rows minus 1 is 1. 3 columns minus 1 is 2. 2 times 1 is 2. So what do we do right here? We definitely reject the null, and if we reject the null, there is evidence for the alternative. So I reject the null, there's evidence for the alternative, and if I fail to reject the null, there is not evidence. So we check our answer, and we got it. So I think Carson, thank you so much. We're going to hop to Carson's question now, and let's do it. Carson's question is, we have officially made our first dollar on YouTube. April 22nd, 2020. We have made $1 on YouTube. It took us 1 week. No, it took us more than 1 week. It took us right about 1 week. $1 on YouTube has been made. Carson, was this a Chapter 17 quiz or homework? Chapter 17 quiz or homework, Carson? The researcher's question. I think it's 17 quiz, right? Oh, thank you, Lindsay. I appreciate it. 17 quiz, you got it. And then tell me if I find the right one. Just keep watching videos, liking videos, commenting on videos. The more you comment, the more you like, the more the algorithm thinks that we're a good channel. I'm not saying we're not, but I mean, we are a good channel, but it's $1 in a week. By 2 years from now, you only get paid if you get $100. Like, you can't get paid if you have like $20. They won't send you $20. You have to have at least $100. So in about 2 years from now, we can achieve $100, and we can then get the money out, and we could have a pizza party with $100. So all that good stuff right there. Uh, we have 1 year. We're 1 year away from 2 years. 2 years away because every week $1. So, but it's you guys. It's you guys helping out the channel. I'm not watching all the videos. It's you guys utilizing the channel right here. Here we go. A researcher. Is this the one right here, Carson? So you guys are the ones who humble brag. You guys are the ones helping out the channel. Researchers collected samples. Is this the right one, Carson? I think it is. Oh, it's not the right one? Okay, then. Nope. Ah, is it right here? Researchers investigated the size of a water glass? Is this right? Here we go. I think we got it. Okay. So for this one right here, we need to make sure we know all of our notation. Now, it gives us the notation, but we should mark it even more. Always mark your notation. Let's go ahead and take our notation. And notation. So there we go. We have our notation. We're going to go ahead and put it into a worksheet. Let's go ahead right here and make sure we know what is what. Okay, got nice and zoomed in so we can write legibly for once. We go right here and we have the sample size 1 and we have sample size 2. We have the mean of group 1 and we have the mean of group 2. We have the standard deviation of group 1 and the standard deviation of group 2. So we've got everything here properly marked, and we know what's what. This or this. That's what we know. Cool. And so we have all of the notation. Now we just have to know the equation we're using. We want to look to also see what we're testing about these glasses. This is where I think mistakes can happen. Did the glass size change the proportion they use? The portion they use, not proportion. Did the glass size change? So what would be the null hypothesis? The null would always have the what sign, Carson. The null always has the what sign. Whenever we write a null hypothesis, the null has the this sign. The null has the this sign. The null has the equal sign. You got it. So we know the answer there. And then we want to see if it changes. We want to see if there's a change between the two. So if we want to see if there's a change, what would be the alternative to see if there's a change, i.e. difference? So we want to see if there's a change or a difference. What alternative would we use? Because we're investigating, does it change it? We're not asking if it's more or less. We're asking if it's... So we want to see if it changes, if it's different. Yep, does not equals. You got it. Nice job, Carson, right there. Because you have to look to the question. The question always tells you what it's asking for. Does it change? Is there evidence of a change? So we're going to say that it's the same as the 2 and that it's different, because that's what does not equals means. It's different. So now it wants us to do a t-test. So now when we do this t-test right here, we have to find first the t-statistic. So the t-statistic is going to be the easier part. The p-value is going to be the tougher part. Not that it's tough, but it's going to take a moment. So the t-statistic will be calculated the following way. And once again, we have these formulas on the test. Never hurts to memorize them or have reference to them to use. It is, the t-statistic is going to be, our t-statistic is equal to, we'll do it on the other side here. We'll do y bar 1 minus y bar 2 over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is equal to a t with a certain amount of degrees of freedom. So all we have right here is just the two means are subtracted up top. So you can tell here that the two means are like 4.92 minus 6.78. The small glass is mean 1. And then we need to solve the bottom of the equation. So I'm going to go ahead and solve the bottom of the equation right here. And let's do it. So we need to do standard deviation 1 squared. So standard deviation, chapter 19. Yep, we can do upper roll. You got it. I think another person had, Abigail or someone had a question too. Joel has the serial question. We'll do serials, and then we'll do, I think, Macy, your question next. And please remind me if I forget of someone's question. So there's S1 squared, and then we divide that by the sample size. I'm going to copy this for right now. That right here, what I just solved this. So I just solved that. Now I'm going to do S sub 2 squared, and this is basically 9, basically. If you misclick, you make an error, so hopefully I don't make a mistake, because I clicked a bunch of buttons there. That is that one right there. We're going to add that to the other one. I've now solved for this portion right here. So what do I have to do next? I have to square root it. So now I square root it, and I've now solved for everything inside of here. So I'm going to copy this for the moment. So now that is the answer to the bottom of the equation. All I'm going to do is take the mean on the top. So let's do this right here. We take the mean of 4.92, that is the mean one, if you notice my notation, minus 6.78, and then we divide by, and we get a t-score of this, negative 2.687. So we're going to copy this right here, and we're going to bring it back over. We just did the easy part. You're like, wait, we did the easy part? It's not really any of this, but it's the less. I just wish there was an easy way to get the degrees of freedom. I guess we had solved the formula for it, but I never like solving for the degrees of freedom. It's like my least favorite part. I like interpreting data. I like making graphics. But I will say this problem right here has an issue. It's one of the few Pearson questions where you might get it wrong, and I easily will give you points back. You need to use the following applet to get the answer precise on this. And I should put it in the comments on the question. Updates are needed. But because, and I think they changed this recently, because you need 4 decimals, we're going to need a few applets to help us out here. So the applets we need, we've got our 1 applet. So, and let's grab the other one. Okay. This is the first applet we will use right here. And so they're both in the chat right now. And here is the 2 sample t degrees of freedom calculator. So notice how this has sample size 1, sample size 2, standard deviation 1, standard deviation 2. So let's go back to here, and we have 27, 25, and then 1.81, 2.99. So 27, 25, 1.81, 2.99. Okay. 27, 25, 1.81, 2.99. If I got it incorrect, because I couldn't remember the numbers. So we have these numbers right here. This gives us the degrees of freedom. From the degrees of freedom, we go back over to the t applet, and we put the degrees of freedom in, and that's going to draw out the t distribution for us. So you have to know your degrees of freedom to know how your t looks. The degrees of freedoms change how the t looks. Different degrees of freedom make your t look different. So when you change the degrees of freedom, you change the way the t distribution looks. So now we take our t statistic, and I know that says x, but we put it inside of here. Now, I've done like a very exact calculation on this. Hopefully it doesn't get mad. I need to pick the two-tailed test, which it's very hard to see, but this is a two-tailed test. I'll have to scroll over. You can see the area underneath it right there under the 2 tails outside of my value. So this is a very, very small p-value of 0.0105, and that's the 4th decimal, and hopefully it doesn't get mad at me. This one is probably one of my least favorite questions. I'm responsible for all the questions, so you can be like, Brian, why'd you do it to us? Why'd you give us this question? I'm sorry. It's so exact, and any sort of rounding, because here's what I'm worried about. It says to round this to this, so I want to see something. If I put in this value, well, it should like it because it's the same number. So 0.0105. And please tell me if you're off by a decimal. I will always give those points back. So what do we have right here? We're using an alpha of 0.05. So using an alpha of 0.05, would I reject or fail to reject the null? Pause the video right here and think your p-value is low. Would you reject the null? Your p-value is low. Would you reject the null? Who knows? The p-value is low. Do I reject the null? The p-value is low. Do we reject the null? The answer would be silence. The p-value is low, so we definitely reject that null. And when you reject the null, there is evidence for the alternative. So there is going to be evidence. Always try to do it without their help. Always try to be like, oh, my p-value is lower than alpha. My p-value is lower than alpha. I reject the null. That means there's evidence. This provides evidence that they are different. Now be careful. You might be like, well, I saw, could you work through questions 3D and E? I think we did a double check, and Brad, we'll come back to that here in a moment. We're going to do a few more of my Pearsons, then we'll probably come back to project here in a moment. And thank you so much. So does this make sense here, Carson? Hopefully I got everything right. 100%. I always get afraid when I hit that button. So we would reject the null and say we have evidence for the alternative that they are different because we chose up here earlier. They're different because the glass sizes, we wanted to see if it changes the proportion. And I think someone had, Rachel has a question. We have epidural, we have chapter 17, and serials. Okay, let's do serials first. And then, so now we got the serial problem. Here we are with the serial problem right here. This problem right here, so this is going out here to Joel right here. Oh, you mixed it up. Did you get it fixed? If your p-value is low, reject the null. That provides evidence that they are different. If your p-value is high, then you do not reject the null. That would not provide evidence that they are different. Does that make sense, Carson? If your p-value is higher than alpha, you do not reject the null, and then you do not have evidence that they are different. If your p-value is low, you reject the null, and you have evidence that they are different. Does that? When the p-value is low, reject the null. When the p-value is high, just let it fly. So, continuing on right here. We're going to copy this data. We're going to bring it over to Jump right here. So let's grab this data. Now, once again, anytime I do, you're welcome, Carson. So glad to help out him. Did you get it right? I'm hoping you did. So we're going to copy this data. But please remember, when I put stuff into Jump, follow exactly what I do, or as close as you can to it. Don't change up what I do. You want to go here to New Data Table. Now, as soon as you click New Data Table, don't type anything. You're just going to expand the window. Don't click inside of it. Just, okay, we're good. So I'm not clicking inside the window yet. I'm going to go to Edit, Paste with Column Names. Great job, Carson. I'm going to go to Edit, Paste with Column Names, and I've done it correctly if they're both quantitative. So does everyone notice here that we have two quantitative because it's blue? If it's blue, you've done it correctly. If it's red, you've done it wrong. This one right here behind me right now is incorrect, and I'll need to start over again and paste with column names to do it correctly. Rewind the video if you did it incorrectly and make sure you see blue, which is correct, and not red, which is wrong. So let's make sure we're using our correct way of doing this right here and go to Analyze. Oh, we got to do one more thing. We got to go to Tables, and we got to go to Stack. Tables, Stack, and double-click both of these. Click, 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 click. Go ahead and click OK right now. Now that we've clicked OK, we've got the data we can work with. It has here the categorical variable, because this is a two-sample t-test, and it has here the quantitative value, which is what we're going to analyze. This right here is the y value, and this is the x, because we want to see if the label on the cereal can explain the sugar content. So we go here to Analyze Fit Y by X. We put data in the y, and we put label in the x. We click OK, and we go to t-test. So all I did previously is I put the categorical variable in the x and the quantitative variable in the y, because we're doing a two-sample t-test. And now we will see the difference in the means. So what this test does is it figures out what is the difference between the mean we observed with children's cereals, which was a much higher mean, versus the mean of adult cereals. It's analyzing the difference between these two means, which can be kind of seen right here. I do not suggest using this test, but this will help us see it a little bit better. We're not going to do an ANOVA today, but you can notice here that this is the mean here at the center of this diamond, and this is the mean here, and that's what we're doing. We're not going to do the pooled t, analysis variance. Don't do the ANOVA test. You will not get the right answer. So I'm going to remove the ANOVA test. Cool. But it was just easier to see that the means were around here, and that's the difference we're analyzing. But we do get the confidence interval right here done assuming unequal variances. So we're doing an unequal variance t-test right here, which is what I would suggest. I just don't know why people assume equal variance. It's like better to assume unequal variance, in my opinion. And we get the following right here. Do consumer, and we'll do that one next here, Oliver. I think we'll wait. Yeah, Oliver, you couldn't make it this morning, so we'll do Oliver's next right here. And that's the chapter 17, so that's really good, because we'll skip here, and then we'll do epidural and stuff. Great questions, Oliver. So if you see right here, the interval is 31. Yep, you got it, Oliver. 31.83 to 40.39. Let's go back. Back. 31.83, 40.89? No, it wasn't that. It wasn't that. That's way off. 40.39. There we go. Oh, man. My brain. I was remembering numbers earlier. Now I'm just like double guessing myself. 3.9. And then with this, we would say that with 95% confidence, children's cereals have about this much more than adults. I do want to point out some stuff. Please realize that in the lecture videos, I go into a lot more detail on this. But let me do the last little bit of this question right here and show you some stuff. Do we type all the numbers in? Good. As long as we type everything in the right way, we will be good. So you should know what all of this output is. For anyone watching this video right now, please don't stop the video. Don't be like, oh, I got it right, I'm done. No, you should know what this output is. So let's take a look at this output right here. Let's drop it in here. So you can easily write your null and alternative for this by doing the following. You can just write here mu, and you literally have the null hypothesis that the mean for children's cereal minus the mean for adult cereal is equal to 0. The alternative would be, if we're looking for a difference, that the mean for children's cereal minus the mean for adult cereals is not equal to 0. So you've written your null and alternative using that right there. You can see that it's children minus adult. So since this difference is positive, you're basically saying amount A minus amount B and it must be that amount A is the bigger one because there's a positive difference. So that's how I knew that children had more than adults, along with the graphic for their sugar content in their cereal. Lucky Charms, awesome, all I create sugary cereal. And the standard error of the differences, so this right here is y bar 1 minus y bar 2. The standard error of the differences is the part of the equation s sub 1 over s1 squared over n sub 1 plus s sub 2 squared over n sub 2. There we go. So that's the standard error right there. It's that equation I was writing earlier in the video. The upper and lower limits on the confidence interval are just literally your upper and lower limits. And you know what's interesting? I don't think I've pointed this out many times, but this value right here is actually the very center of the confidence interval. That value would be at the very center of the confidence interval right there, and you can calculate the margin of error. The margin of error is kind of close to 4. How do I know that? Well, because 36 plus 4 is 40, and 36 minus 4 is basically 32. Now, it's not exactly 4. You could figure out the margin of error by doing formulas like upper minus lower divided by 2 or upper minus center divided by 2. So this is also known as the center of the interval right here. That is the center of the confidence interval, which is our estimate of the true difference. Now, something I've already kind of shown you by doing this is that if you take the difference and divide by the standard error of the difference, which are these two numbers here, you actually get the t ratio. So this is the t statistic from this formula right here. This t statistic is from this formula. That calculator we used just a moment ago to figure out the degrees of freedom, that is going to be what's solving right here. So when you look at this output right here, this degrees of freedom right here would be calculated using this formula right here, which this does a formula in the background for us. So that's what that degrees of freedom is showing us right here, is what t distribution we are using. These p-values right here are for the following. They are for the does not equals test, the greater than test, and the less than test. Oh, you know, you got it wrong. Send me what you got wrong. No, Carson. Carson, no. We'll get it fixed up. But this explains this output, hopefully, and this confidence interval is a 95% confidence interval. But whenever you have output, and I'm so proud of my 474 students, they saw something in some output yesterday, and they asked me, and I didn't know what it was, so we pulled in Dr. Petrie. We did a phone the experts, and Dr. Petrie, he agreed with, I took a guess at what it was, and it was so cool. He joined the live stream, he helped out, and you know, he's Dr. Petrie. I'm just Brian Stevens. So he knows stuff better than I do when it comes to some pretty high-level concepts. And it was kind of what I thought it was. It was that. Oh no. Did you reverse the way you subtracted them? Was it on the quiz or was it on the homework, Carson? Give it another shot. Give it another shot and see what you got. And give it another shot. Just check the work. Make sure each thing is labeled properly. And give it another shot. Email me and we'll figure some stuff out. Oliver wants the one on, do consumers spend more at A or B? It's gonna be really sad if I know this is question number 10. Oh my gosh. I've done these questions a lot so far. Okay, we'll do it. You got it? Here we go. So what we need to do right now is we need to know our notation. Every time you see one of these, you need to get your notation. It's like number one goal with any problem is notation, 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 notation. So let's do this right here. And let's do it. Got it? We're good. So we need to mark what these are. We're going to have store A. Let me look at the problem again just to make sure how it has the things labeled. We're going to do A minus B. Okay, cool. So it's A minus B. Oh no, PowerPoint, go away. Okay. So it's A minus B. So this right here is sample size A, sample size B. Mean for store A, mean for store B. Standard deviation for store A, standard deviation for store B. Okay, we've got our notation marked. We are good to go on this. With notation marked, we can go back to the problem, and we can identify the null and the alternative. It wants to know, I believe, if they're the same. So do customers spend more on a trip to store A or store B? So they want to know if there's a difference between the stores. Now, the null always has the equal sign, so this one's eliminated. It can't be this one because the null has the equal sign. And we want to know if they're different. So which one would we want, Oliver? Would we want A, B, C, or D to see if there's a difference between the stores? Look at the alternative. You dispute. Oh no, I'll fix that, Carson. After I get off the video right here, I'll fix it. So I'll fix it because you disputed it. Like, I have no idea. You can redo a homework question though. I have no idea what you mean you disputed a question. We'll get that fixed up here. I'll I'll probably start streaming around 4:30, 4:40 or so. So, which one of these alternatives would I use? Does anyone know? We want to see if there's a difference between the stores. Would I use A, B, C? Oh my gosh, that kills me there, Carson. Who knows what alternative we would use? We want to see if there's a difference. So if we want to see if there's a difference, we would use the does not equals alternative. Always look to the wording. They want to see if there's a difference between the stores, so we'd see if there's a difference. This one hops right into computing the test statistic. So when we compute the test statistic right here, we need to go in and we need to do y bar A minus y bar B equals square root, and then cool, equals S sub A squared over N A squared. Oh my gosh. I can see it in my head, and then I just have to think about what it is. Okay, cool. Too big. Okay. Oh no. Fix it up or wait till I'm done and then I'll fix it up, because that seems like you got it right. You just put in the wrong number. And then, so this will solve for a t with a certain amount of degrees of freedom. So we have to go in now and we have to plug in our numbers. So all I'm doing right here, Oliver, is I'm plugging in the numbers. Does this make sense, Oliver? Are you following along right now? That I'm just going to plug in the numbers and get my t statistic. So this is the formula right here. I've got all my notation marked. So let's go ahead and start putting in S sub A, which is going to be 21 squared. 21 squared is going to be that. And then we divide by 83. Get this right here. We copy that. I just solved this portion of the equation right here. Then we do S sub B squared, which is 18. We square that. We divide that by 82. Just don't type a wrong number. It's so easy to do. And then we're going to add this to this number here. And I've now solved the bottom of the equation. Square root of that's going to be like 3.12. Oh, I was way off. I mean, it's obvious it's 3 something. But we have now found the bottom of the equation. So now we need to subtract b minus a, which is going to be a t statistic about 3.33. Yeah, we'll go back to project here in just a second. You got it, Jacob. We'll do that about 4:30. 4:30 we'll be going back to project help, I believe. 43 minus 53. I did not type 43. 43 minus 53 is going to be 10, and it'll be negative 10. We're just solving this right here. We do this right here, and we get negative 3.28. So this right here is the t statistic for this problem. We just solved for this thing right here. We plugged in all of our numbers and solved it out. So we go back, we plug in the t statistic, we round it to 2 decimals, and we're good on that. Now we need to find the p-value. And the nice thing is, I'm going to guess the p-value here, and then I'll show you how I found it. Our sample sizes are huge, and so our p-value should be question 4e. Yep. If 4e is the last one, check the very start of the video, Caroline, and I will come back to this. But if 4e is the last question on the project, go to the very start of this video. You can rewind time on it. And yeah, go to the very start, and you'll see me talking about it a lot. So check that out, Caroline. And if I don't answer a question, come right back live. You can click the live button at the bottom. You're welcome. Yeah, and you'll see the following graphic. You'll see me talking about innocent or guilty. We have it in here somewhere. I did it again, didn't I? It's here somewhere. You'll see me talking about innocent or guilty. And here it is. Who is that? No clarity. So awesome. And so good stuff. Let's hop back to the question right here. Find the p-value. The p-value is going to be 0.001. I'll explain how I got that here in a moment. And since the p-value is low, I reject the null. There is evidence that the means are not equal. We check our answers. We got 100. We got it. Let's show how we got the p-value right there. And we can do, it looks like Julia might want us to go back. Also, much views on the other computer bounce. Yes, I know. Thank you, Jacob, right there. Glad to help out. And let's see right here. So we've got this all figured out. And then let's hop back over to, where was it? The way, my brain just broke. You might say, how did I know the p-value? Well, here's my sample sizes of 83 and 82. I have to go over here, and I have to type in 83 and 82. And my standard deviations are 21 and 18. 21 and 18. The degrees of freedom here are going to be something like 156, 160, basically. This is a very large amounts of degrees of freedom, and we're going to go over here to the t-applet now. I like this t-applet a lot. It's just better visually. I'm going to put in the degrees of freedom. I'm going to put in the t-score. Now, this basically looks like the normal. This is so nearly identical to the normal that when I do the two-tailed test on it, the p-value is going to be very, very small. It's basically the same as the answer would be on the normal curve. If I go back to the normal curve and I enter in a z-score of this, it's the same answer basically. It is different. I have to re-enter the degrees of freedom that were basically 160, use the exact number it gives you, and then I have to re-enter the t-score and do the two-tailed test, which we see right here. You can't even really see it. There's area underneath here, and there's area all the way over there. If you don't trust me, there is area outside of the tails. It just gets so small you can't see it, and it's like 0.001. So I knew it was going to be a very, very small p-value, and that's how I was able to guess it, is because I knew outside of 3 standard deviations, it's only 0.003, and we're beyond 3 standard deviations. So I knew it was basically probably 0.001 or 0.000. It's small enough that it's barely unnoticeable. So hopefully people realize with my knowledge of the normal that outside of a z-score of 3 is 0.003, and that's on both sides, total outside of 3. Knowing this, I was able to say, well, we're further out, the p-value is going to be smaller, and the degrees of freedom are such that it's basically the normal curve. So that's a little bit of stat theory for you right there, and we got that one right. I think there was another, I think the epidural one, so this goes out to, where was the epidural one? And we did Storia and Sorbia, right? I think we did. Yeah, we just did Storia and Sorbia. Let's leave the question on screen. And Macy wants the epidural question. Let's do the epidural question, then we'll hop back to project for just a little bit here. We'll be right on time with it. Chapter 19. Is that the quiz or is that the homework, Macy? Chapter 19. Let's see. Epidural. I think we found it. So we have found it. Is this the right? I think there's 2 epidural questions. Homework. Oh, wait. Then we got to go to homework. Okay. Yep. Here we go. I think this might be very similar. Cool. We got it. Let's do it. Let's do this question. So what kind of test would be appropriate for this? This is the chi-squared test of independence to see if the if someone's breastfeeding at 6 months is independent of epidural. And so we will take a look at this right here and see if they are independent or not independent. So we are doing the chi-squared test of independence. You think I'll do this one real quick and then we'll do the next one. How's that sound? This one might be the, I think one of them is easier and quicker. So we'll do this one right here. Write the null and alternative. Breastfeeding at 6 months is independent of epidural. So breastfeeding success is independent of having an epidural. And then breastfeeding success is not independent. So there is an association. This is a tricky one right here because it doesn't say that they're not independent, but it means the same thing. So I'm glad we did this because saying that things are not independent means that they are associated. To say this is not independent of this means that they have some sort of association with each other. So we would say that they have an association. So this is breastfeeding success is independent of having an epidural. Breastfeeding success is not independent of having an epidural. I like to do it that way because it's really easy. Okay, cool. Now we're on to the next one. So I guess it's not too hard to get that one right because you can do it multiple times. So how many degrees of freedom are there? Macy, I need your help. This is a what by what, so it's going to be how many by how many degrees of freedom. This is a what by what, so it's how many by how many degrees of freedom. So scores and standardized tests were, yep, we know we're next to Oliver. It's 1 degree of freedom. So if anyone's wondering this trick, it's a 2 by 2, reduce it to a 1 by 1, which makes it 1 degree of freedom right here. So we got this right here. We got that. We'll do that one next year, Oliver. You got it. The smallest. Okay. So the trick for the smallest is to go to the smallest row total and the smallest column total. So we need to take our data, bring it over here to Word, and let's put it in. And then where would we have the smallest row total and the smallest column total? Which one of these? Epidural has the smallest where? Epidural has the smallest on no or yes. Now be careful. Well, it does go that way. Epidural has the smallest on no or yes. Which one is smaller, no or yes? You're right. This one is smaller on epidural. It has smaller here. And then the other one, is it smaller on yes or no? For this one right here, is it smaller on yes or no? And it is smaller on no, I believe. This is the one we'll be doing right here. Now, it just happened that it's the smallest. Like, this being the smallest number here is just coincidence. That is simply coincidence right here, and that's not the answer because of it. The answer is because this is smaller than 703, and this is smaller than 778. So we would solve this equation right here because it's row total times column total over grand total. Being that this right here is the row total, this right here is the column total, and this right here is the grand total. Row total times column total over grand total, and we can draw it right there. So let's go ahead and solve for the smallest expected cell count, which is going to be, good, not blocking it, go way up here, 471 times 369 divided by 1174. We got that right there. There is the smallest expected cell count. We've done it. Go back here, the smallest expected cell count rounded to 2 decimals. Got it. Check answer. Well done. Continuing on. What are the conditions? Now, they always do this. They always break the independence assumption. It's not a condition, it's an assumption, and the randomization condition apart. So these are condition 1. Condition 1, random. Gotta do it. So condition 1 is random. Condition 2 is 10%, less than 10%. Condition 3 is count data. And then condition 4 is expected cell count. There is no numbers to the condition. They're all just conditions, but I like to do them in order because condition 1 and 2 can always be the same then. And you notice here that the smallest expected cell count is greater than 5, so we're good. If the smallest one is larger than 5, we are good. So we should be good on these. I was hoping I didn't misread them. Oh, we got it. That's got it. Awesome. Cool. Good stuff, Macy, right there. Cool. Awesome. Sports. So we're going to go back to Oliver's question here. Then we'll do some project stuff. So we're going to do project at this. I said project at 4:30, so we'll probably have project people back in. You're welcome, Macy. Glad to help out. Let's see right here. And I think Oliver said it was a quiz question. Last question on Chapter 17 quiz. Okay, cool. Chapter 17 quiz. Chapter 17 quiz. Okay. Place questions. And the question was the scores on a standardized test. Aha. The scores on a standardized test between these 318 non-traditional math classes were compared to 277 students in traditional math classes. Computer software was used to create a confidence interval, 98% confidence interval, and we took the difference between these scores. Now, if you notice here, the interval, I always try to make it easier by just using numbers a lot of times. It goes from 5 to 11, or you could say from 5 to 10. Now, don't round it that much. But if you think about from 5 to 10, what does this mean? And I've seen a lot of people have a little bit of a disconnect. Oh, yeah, Lindsay, if you want to mind, please email me and I'll fix that, Lindsay. But yeah, so don't worry. That's ridiculous. Hopefully you're one of ours and I can fix it pretty easily. I'm going to go check emails probably around 5-ish. You need to eat, check emails, and drink some orange juice or something. But yes. And what were we saying? Oh, yes. You're cracking me up. Okay. So this problem right here, we have the interval right here from non-traditional to traditional. So we have mean, oh, you see, it's not highlighter selected right now. It's tricking me. Mean of non-traditional minus mean traditional minus mean of traditional. So we have the mean of non-traditional minus the mean of traditional. Now, I used an example yesterday I think it was really good. It's like if I play my brother in basketball. So you've got the mean for Darren minus the mean for Brian. And we're going to see how many points we score in a game. So what if this interval was something like, so I want help with this. You guys got to help me out here. What if this interval was something like 21 to 5? And we look at how many more points Darren scores than Brian, like the difference between the points Darren scores in the game versus Brian scores in the game. What would this interval from 21 to 5 mean? What would this interval from 21 to 5? We could do it the other way because it'll get mad sometimes you put them in the reverse order. What does the interval from 21 to 5 mean? Or 5 to 21? And why do you know it's this person? Why would this be who's scoring more? I need help here. Who's watching and help me out? How do I know who scores more and which one of these would be higher? And why? Any ideas? Any guesses? Who's better at basketball, Darren or Brian? And this interval shows it. Because I am 95% confident the true difference between the amount of points that Brian and Darren score in a game is contained in the interval. Oh, I wish it was Brian, but it's not. Good job, Oliver. A million points right there. I'm 95% confident the true difference between the score that Darren and Brian will score in a game is contained in the interval 21 to 5 points, with Darren scoring more than Brian. Since Darren is the first number, if Darren were to score something like, and we need to do it right here. So if Darren were to score something like, let's say hypothetically, Darren scored 20 points and Brian only scored 10 points in a game, then we would see a positive difference. But if the interval was negative, then we would see that Brian scored more than Darren. Do you see right here, in this instance, Brian is scoring more than Darren and the interval is negative. And I guess I should be careful because now the interval should be centered at 15. For the example, it should be centered at 15 now. So this is what we observe in a sample maybe. So what we did is we took a sample of students and we saw what we observed. So when you look at this right here, who is scoring more? Who is getting higher scores? Non-traditional or traditional? Remember, the interval is positive. So which of these groups scored higher? Was it the students that were non-traditional or traditional? Because the interval is positive, remember how the Darren Bryan example worked? Because the interval is positive, which of these two means was higher? Because the interval is positive, which of the two means was higher? It'd be non-traditional. Non-traditional would be higher because it's the first one, because it'd be like 10 minus 5 is a positive number, but 5 minus 10 is a negative number. Great job right there, everybody, 1,000,000 points. And so what do we get? And thank you guys for participating. I love it. You guys can tell I pause when no one gives answers. I'm like, no. So what it is right here, just plug in two numbers to this. So let's go back. Let's review. If we take this right here, and let's just do pretend numbers. And if we put this in right here, and if we did something like 10 minus 5, would that be a positive or negative number? 10 minus 5, would that be positive or negative? Would 10 minus 5 be a positive or negative number? It'd be positive. What if we did, magic color change pen, what if we did 5 minus 10? This would be negative. Now, what we're trying to do is we're trying to estimate the true difference between the groups, like which of these do better on average. So if we see a negative interval, which of the two numbers was bigger? If we see a negative interval, which of the two numbers was bigger? If we see a negative interval, the first or the second was bigger. Space pen returns. If we see a negative interval, which number was bigger that we used to make our interval? A negative interval would indicate which number was bigger. The second, you are right. And if we see a positive interval, it's because the non-traditional scored higher on average. Does that make sense? So the negative interval would indicate that traditional scores were higher because we do number A minus number B, and the second number would be larger, making a negative interval. Or if the interval is positive, it's that the first number was larger. Does that make sense? Because if it's 10 minus 5, it's a positive interval. And these are just made up numbers to kind of show, like, if the first number is larger, you'll get a positive interval, or the interval will be mostly positive. If the second number is larger, you'll see negative numbers in the interval. And that would estimate that the second number is larger. Does that make more sense, Oliver? How are we doing on that, Oliver? If it's 5.1 through 11, would that mean that traditional... No, it would mean... So if it's 5.1 to 11, then you would think that the non-traditional students scored between 5.1 to 11 points higher. The non-traditional students would have scored between 5.1 to 11 higher. Because, is it minus? Oh, if it's minus... I thought that was a through right there. Through minus 11, do some of the... Double check... Let me see how my question looks. I don't think the interval is usually that wide. Let me see how the interval looks. So there is a minus right here, Oliver. It says 5.1 through minus 11, does it? Double check, because I don't... Or does it say 5.1, comma 11? My guess is it says 5.1, comma 11. I haven't seen... Because usually if it's the minus, they'll put the minus first in the interval. So I think... yours is like mine. If it is, and there's no minus here, then this would indicate that the non-traditionals are higher because the interval is completely positive. Does that make sense? And here's a big question, Oliver. You ready for this one? I bet we got this one. You ready? How do we figure out the margin of error of this interval? What is a formula I can use to solve for the margin of error? We basically have 5 and 11. So I'm just going to do a simplified version of this for now. If my lower part of my interval is 5, and the upper part of my interval, but wouldn't it be? Oh, I think you might have. Sorry, thing might have missed. This right here is the mathematics being done. This is not. So I think I know where I might have confused you. This right here is not the interval. This is just the mathematics being done. So this is not. These numbers right here create the interval. So when you do this right here, this is not actually the interval. This right here is the creation of the interval that, here, I'll explain deeper about it. So it's like, maybe this is like a test where these students right here made an 88, and these students right here made an 82, and then these students, this is an example A, example B, and on this one, these students made an 80, and these students made an 86. So now when we create these intervals, I want you to look at these two intervals. So this is the confidence interval we're going to create from it. This top one right here would maybe have an interval that goes from 3 to 9, and that's the interval it creates. And this interval right here is going to go from -9 to -3. So this is the mathematics being done on the left side. And so in example A, we think that the scores for non-traditional students would be between 3 to 9 points higher than traditional students. In example B, we think that the scores for traditional students might be between 3 to 9 points higher. If you notice how in example B, the traditional students had a higher score, and so the interval is negative. And that's awesome, Oliver. I like it when we see that right there. Can you tell me what the center of these intervals are? What is the center of this interval right here, and what is the center of this interval? So you've got answer 1 and answer 2. What are the centers of these intervals? What is the center of interval 1? And you'll notice it might be something like that, 6. And then what is it's just the difference between the two means. You're right. You got it, Oliver. You're getting it. So if you notice, that is the difference between y bar 1 and y bar 2, because this is y bar 1 minus y bar 2. I know it has this up here, but that's what the interval is trying to estimate, and we're estimating it via the sample. So we're trying to estimate the true difference, and we use the sample to estimate that. But now be careful. I'm going to give you another question right here that's very similar to this, and I want you to tell me, here's the mathematics, which you don't really get to see all the time. So right here it is, and then we'll go -1 to 5. Okay. So look at example C now. So in example C, I want you to tell me non-traditional might score about this much higher, or traditional might score about this much higher. So first question, non-traditional might score about this much higher, or maybe it is that non-traditional score or traditional scores about this much higher. Very, very tricky to say all these words. So you notice this interval goes through 0. So 0 might be the difference between them. Also, I made the margin of error the same as the previous ones. If you notice that, all of these have the same margin of error. Let me put that as a note right here. I can't write that small. Scores 1 less or 5 higher than traditional. Let me see that. Yes, you got it right, Oliver. You are correct. That is it. Because you could just phrase it in the terms of non-traditional. Excellent work there, Oliver. That is what we estimate it to be. It's not that we know that. It's just we're saying, like, what do we think might be the scores for all students? So we don't know that this is the truth. We might be 95% confident that non-traditional students will score between 1 point lower or up to 5 point higher than traditional students, because we're trying to estimate what the truth is. So excellent work, Oliver. I think that, Oliver, that is amazing work. This is the same center. Oh, no. It's a negative center. I shouldn't write that. That's an error. Not the same center. This has -6 center. -6 center. I'll put it in the center here. -6 center. Oh my gosh, what am I doing? 6 center, -6 center, and this has a center of 2. They all have the same margin of error though. So every one of these has the same margin of error. This difference of 2 is what was used here. -6 right here, and 6 was used here to create the center of the interval. Because the center of the interval is y bar 1. We'll write it in right here. It's y bar 1 minus y bar 2 plus or minus t statistic with the right amount of degrees of freedom. And then we go and we do square root s sub 1 squared. Good, I'm barely going to block it. Project after this. Project. No, I'm not blocking it. s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. That's got it. So that's what's doing the mathematics to create all these intervals right here. And this difference right in here, these differences are literally what creates the center of the interval. And these margin of errors, all these margin of errors are being created by that. That's all the margin of errors. So that's a really good kind of quick review of all this. And we get to our last question right here, or the last thing we really need to understand about this, is a very big concept about margin of errors. My interval right now goes from 5 to 11. So I'm rounding the numbers, making them nice and neat for myself. If I have an interval that goes from 5 to 11, Oliver, how would I solve for the margin of error? Did you do the weapon question during office hours? Yes. Did I do it this morning or yesterday? I think I did that one yesterday at the end of yesterday's video. Check out yesterday's video, Lindsay. Go towards the end of yesterday's video in the final hours of it. We did the weapon question. I think we did both of them. So we did both weapon questions. We didn't do the college admission one. Very close, Oliver. That'd basically be what it would be. It's going to basically be that. It's going to be 2.5, I think, or at least the way it's written here. You're welcome, Lindsay. You can take half. What we're going to do is we want to take half the distance of this because the margin of error is this right here, and the margin of error is this. And so I just do upper minus lower divided by 2. So upper minus lower divided by 2 is equal to the margin of error. And think about this formula. All this formula is doing half the length of the interval. So the length of the interval here is, Oliver, you were right. Oliver, 10 million points. Excellent work. It is 3 because it is 6. I just can't read today. The easy math is the hardest part. Oliver, you were 100% right. You were like, wait a minute. It is 3. It's upper minus lower divided by 2. You are right. That is a distance of 3. I just don't know how to math. So very good job, Oliver. It's so easy to make common mistakes. That's why we double check our work, and we're all capable of making those mistakes. So let's do the formula right here with the same interval. We just need to do upper minus lower divided by 2. There's the margin of error. Now, if we go from a 98 to a 95, we're going to make the interval tighter. So 68, 95, 99.7. If you go from a 98 to a 95, the margin of error would decrease. All of these are going to get smaller. Everything would get smaller. And you're wondering why? Well, 98 looks like this. 95 looks like this. When you go, mine is going 98 to 99. So would that increase? Would that make things larger and increase it for going from a 98 to a 99? And make sure it's from 98 to 99. So this is what it was, and this is what mine is. So yours should have 98 here and 99 here. So what would that do to your interval? Would that make it larger and increase it, or smaller and decrease it? If you're going from a 98 to a 99, think about if you're saying you hold 98% of the possibilities and you're going to go to 99% of the possibilities. Larger and increase. You got it, Oliver right here. Like, I got a nephew named Tolliver, so this, yeah. Can you please go over? Yeah, Jacob, you got it. Jacob, we'll do that next here. This is the big mistake people make. Is it students in non-traditional math classes? It's not a student. Well, since the interval is going to increase, our margin of error would increase, and the critical value we're going to use to create it. When it talks about the critical value, it's actually talking about this value right here. This is the critical value that controls the margin of error. So the critical value will increase and the margin of error will increase for your problem right there. So this t becomes larger. Like a z-score for a 68 is 1, then z-score for a 95 is basically 2, and z-score 99.7 is 3. So every time you go out a z-score, you increase the critical value for the confidence interval, and t works the same way. You'll make the margin of error bigger by increasing the t, which increases the confidence level. The t is directly connected to the confidence of the interval. Woo, good stuff. And now, does this, let me double check. Students in the non-traditional, cool, we got it. Does this suggest that students who learn mathematics with non-traditional will have significantly higher scores? It's good evidence of it, yes, because the interval is entirely above 0. The interval above 0. It is strong evidence. Check answer. Got it. Got him. So we did it. And let's continue on here. So what about the previous part? Oh no, which part, Oliver? Part C. So what you're looking at right there is, remember, it's students. We're not testing for one student. We're testing for all students. We want to know that the mean for all students is above a certain amount, or that the non-traditional score above this amount. So look it over. Remember, it's only the ones that say students, And then we're talking about how much the non-traditional or traditional above a certain amount. So check that out right there. Does that make sense, Oliver? Ask a question you got in the chat and we'll do it. And then I think Jacob wants 3D and 3E on the project. Let's hop back here to the project, Jacob. You got it. Oh my gosh, look at all those sheets. Did I? When did I do it? I can do the weapon question one after this. So I know I did it, but we can do it again. We got it. Post the very start of it in the chat here, and it's like the injury one. I know I did it recently. Things are getting fuzzy. And so let's go right here. Question 3D and 3E. Awesome. We've got a test up like this. Jacob, do you have your output for 3D and 3E? Do you have your output for 3D and 3E, Jacob? Do you have the output? Yes. Awesome stuff. Okay, I'm going to make some output here that'll look like yours. So here we go. So the value you will be testing is 3,600. So let's go here to test mean, and we go to 3,600. Oh, what am I doing? My output's different than yours, but you'll put that in there. Huge hints. Let's put in the value of 7 right here. Now, I'm going to make 2 outputs right here like you're making. I'm going to remove my Quantile plot because we won't be using that on the project. Nothing in the world if you do, but it's not very helpful. And I'm going to put 7 in here. Now, I get 2 different outputs right here, and they lead to 2 very separate... I want to put it over here. Sure, we're not going to have that happen then. I get 2 very different outputs, and they lead to 2 very different results. So let's start looking at these results for 3D and 3E. So here's output number 1, and let's get output number 2 in here. Output number 2. It's very important to know what all your numbers mean, and then it'll help you interpret what's going on right here. Now, once again, I'm not doing the exact version of your question. I'm doing something very similar. So let's go here and go wrap text behind, and let's paste again, and then let's go wrap text behind text. Cool. Okay. So here we are. Now, both of these are going to have the same null and alternative for me. So both of these tests are going to have the exact same null and alternative. So I'm doing something very similar to what you're doing. My null and alternative, which is not your null and alternative, is that the mean for the tip people will give is equal to 7. This is mu naught in your output right here. That is mu naught. And this is going to be y bar for this one. This is y bar. There's the degrees of freedom, all that good stuff. The alternative would be the following, that the tip amount is greater than 7. So we have that the true mean of tip that people give for card, this one is card, and this one here, put card center in, 7. Card, and this is cash. Okay. So we have that we are testing to see if the true mean of card is greater than 7, and we're also trying to see if the true mean of cash is greater than 7. Now, you always have to slow down here, and you have to remember how we find our p-values. Our p-values here are related to the alternative we are using. So whenever you look for your p-value, you must look at the sign. Now, there's a little trick, and unfortunately, this is the does not equals. This is the greater than, this is the less than. So for all of these tests, do I want to use the first, the second, or the third p-value? For all of these tests, do I want to use the first, second, or third p-value? Which p-value do I want to use for all of these tests? First, second, or third? You are right. The second, you are totally right. Great job there, Jacob. So you might be like, well, what's going on right here? One of these p-values is really high. Well, I want you to think about this. Who here can interpret what the sample mean means right here? This is the sample mean. And what does that sample mean I observe for card tips? What does the sample mean that I observe for the card tips? When I watch people give their card tips, or when I took data on it, the card tip was on average what amount? It was $4.97 on average, basically $5. So we see around a $5 tip for card tips. Now think about this. If you were to witness people make tips on cards, and then you want to see if the tip amount is greater than $7, and they're only tipping $5, do you think you would have evidence for this right here? Do you think you would have evidence that they're tipping more than $7 when the sample mean their tipping is not more than $7? No, you would not have evidence. You'd be like, well, wait a minute, we don't have evidence for that because in the sample they weren't even tipping that. So how would we have evidence that they're tipping more than that if in our sample way up there, the highlighted number, they're not even tipping that amount? You could have evidence, which we're not doing this, you could have evidence that they're tipping less than $7. So if you were to do a less than alternative, which don't do this, I'm just showing you, if you were to do the less than, you would have evidence that it's less than. You definitely do not, and remember this is what we're doing, you definitely do not have evidence that the tip amount that people are giving exceeds $7. You definitely do not have evidence of that. We would not reject the null. We do not have evidence that people are tipping more than $7. Imagine your friend says to you, our company will go to card tips only if we have evidence that we can get more than $7. Do you think they should go to card tips only, or do you say, no, don't do that? They're going to say, if we have evidence that we can get more than $7 on card tips, we will go to card tips. You'd say, no, you don't have evidence of that. No, don't do that. You do not. Your tips are way lower than that. Actually, in truth, you have evidence that it would be less than $7. So we do not have evidence that it's more than. You would not reject the null. And always think about the alternative. That's the important statement. We do not have evidence that you would make more than $7 on it right there. And so it is going to meet the nearly normal. Check back, Oliver. Look for a part in the video. It's towards the start, maybe the first 30 minutes. Ooh, we got so many things open now. Look for the part in the video, Oliver, where I'm talking over this right here. So look for the part in the video where I'm talking over this, and you'll see me explain it. And I did it this morning too, and I'll come back to that here in a moment if you need. So for card, we fail to reject because no evidence of, more than 7. So remember, this is the value we are testing right here. There's not evidence that it's more than $7. That is the tested value that we're trying to see if it's more than 7. This is what we observed in our sample. So what we observed in the sample was not good enough evidence to suggest to us that the tip amount for card is more than 7. We do not have evidence for the alternative. We fail to reject the null. There's not evidence that someone will make more than $7 getting card tips. Does that make sense right there? Because that p-value is very high. And yeah, Oliver, Lindsay gives Lindsay great advice in the chat right there. Jacob, let's make you a mod too. You get some mod powers here, Jacob. You appear to be a stat to oneer, so you get mod powers. Then when you go over to this test, we look right here, and if you look at this, the mean for this is higher. The mean for this one is higher than the hypothesized value. Now, don't obviously be like, oh, then that's evidence. It could be evidence. We have to find out how probable this is or something more extreme than it. And you'll notice it's pretty far off the curve, and the p-value there is pretty unnoticeable. And so now we would say we reject the null for the cash tips, and we have evidence that cash tips are on average more than $7. So what would a type 1 error be in this problem? Kind of doing another review question. A type 1 error would be, especially for the cash tips, since we rejected the null, saying that the cash tips are going to get us more than $7 when in truth the cash tips won't. If we made a type 1 error here, which I just rejected the null, so I'm open to a type 1 error now, it would be that I said that cash tips would make us more money than $7, and in truth, they don't. So that would be a type 1 error in this instance, and I'd be encouraging the company to take cash tips to meet their goal when they should not, because I made a mistake in rejection of the null. I'm like, oh, there's evidence that cash tips, remember the null is true. The null is true. Cash tips actually don't have evidence for this. The null is true, but we're saying we have evidence for the alternative. So that's the good stuff right there. And I think, who else has questions on project or on things right there? Who has questions? I'm going to lean back in the chair. I'm going to fade into the green screen. Actually, how about if I go this close to it? You can be that close to it. You can start to see the reflection on it. Can we do number 4? Which part of number 4? You couldn't find the example? I can do it here in a moment, Oliver. Question number 4, and then we can do that one, Oliver. What about number 4? What part of number 4? Give me 4 like A, B, C, D. Which part of number 4? Well, kind of here. I'll talk about Oliver as well. Awesome. 4C. We'll do 4C. Sarah wants 4C. We'll talk about 4C. And definitely check out, I've got a YouTube video where I show you how to add in the plugin. Let me drop that in the chat right now. Sarah will do that question here, and we'll do Oliver's. Let me pull up. Put that there. Playlist. Project 3 playlist. If you are starting, Where's project 3? Project 3 videos, cool. And here. Do you have a Mac or PC? They're both right next to each other. Where's it? Descriptive statistics on a Mac. Cool. Ah! Did I get it? All right. You got a bunch of people. Lindsay, you're awesome. Thank you for explaining there, Lindsay, in the chat. You're welcome, Caroline. You're welcome, Caroline. Oh, you guys are so awesome. I'm like looking some stuff up, and you guys are so encouraging. I appreciate it. Thank you guys so much. We got 4C right here, and so let's talk about 4C. Sarah wants 4C. You guys just give me the energy right there. I like it. Check out the videos. Throw likes on the videos. That gives me energy too. When I see people are liking the videos or commenting, once again, that helps the channel. Liking, commenting, subscribing, all those things really help out the channel. So I appreciate it. I want as many people to get education as we can. You know, you guys know UT is my #1 priority, but I want more and more people. On 3D and 3E are we using 95% confidence rolls. On 3D and 3E, use the statistical test. 3D and 3C. I think you're talking about 3D and 3E. These questions right here, you will use the statistical test for these. Does that make sense there, Madison? I can show you. You'll be doing statistical tests like we just did right here. So we were just doing 3D and 3E, and you'll use statistical tests like this output right here. This won't be your output identical, but the part of the video we just did right here goes over 3D and 3E. So we got 4C. Sarah's got it right there. The wording is confusing. Let's go check it out. You're welcome, Madison. Awesome work. Thank you guys so much. 4C. A confidence interval can be used to perform a two-tailed test. Any value outside the interval is rejected at an alpha level of 1 minus the confidence interval level. Are you able to reject the value of 3,600 days that was tested in the previous problem? And if so, what alpha level are you able to reject it at? So let's check that out. So when we make a confidence interval, we'll go right here, we'll go, and then we'll do a test using our confidence interval. So here we're going to go and make a confidence interval, and here we're going to do an identical test that would come to the same analogous result. So if we make a 95% confidence interval, we'll do the shading. What would be the alpha level for the test? If we make a 95% confidence interval, what would be the alpha level for the test? Sarah, amazing work. You are 100% right. Now, I want us to think about steak. Amazing steak. Hopefully, I don't know, people might be vegetarians. That's fine if you are. But for me, I'm going to think about steak, good steak dinner. Chelsea and I are going to go out to Connor's Steakhouse, and we're going to go get a steak dinner. And they tell me when I call them up that the steak dinner is going to be somewhere between $40 to $50. Expensive steakhouse. We're going to, quarantine's over, we're going to go out, or be safe, still be careful, you know, support local businesses. I mean, I'm being as careful as possible, but I just want a good steak dinner with my fiance. So she's not here, so we can't do that. So they tell me the dinner is going to cost between $40 to $50. This is a hypothetical example. So they tell me it's going to cost between $40 to $50. And so I want us to think about, if I then heard from a friend, the friend tells me, Brian, I went there and the steak dinner was $10. Would I believe their claim or would I reject their claim? They told me, Connor's Steakhouse told me that their steaks cost between $40 to $50. Would you believe $10 or would you reject $10? And why would you believe it or reject it? You'd reject it. You're totally right. $10 would be way outside the interval right here. It's so far outside that I didn't even draw things for perspective. That's probably about $30 or $32. But it would be way down here and it would fall in the rejection region. Anything inside the interval is believable. If someone told you $42, that would fall right here. And the p-value that when we draw this would not be as small as we need for 5% rejection. So if we had something like a value of 42, we would fail to reject that value because it's inside our interval. But if we had a value that's outside the interval, like any value outside the interval, would be rejected on a two-tailed test with the alpha level of 0.05. Because a 95% confidence interval would be analogous to a two-tailed test with 5% alpha. If you can't see, I'm trying to draw distributions that would add up to 100. Like if you were to add up both of these numbers right here and tell me how much data it is, it'd be 100% of the data inside of this right here. So you can do the same thing. I think about test questions that we should be able to solve pretty quickly. A 90% confidence interval is the same as doing a two-tailed test with what alpha level. A 90% confidence interval is the same as doing a two-tailed test with what alpha level. And 90%. You can continue on, Justin. Don't worry. If you don't meet success failure, it'd be like, well, we didn't meet it. That's not good. But we will continue on. Nice job, Sarah. 10% alpha or 0.10. It's fine to write either way. That's got it right there. If you don't meet the 3 conditions, Justin, still continue on. Still continue on. I think that's got it. And I think we are good. I think it's 5 o'clock. And we did some good streaming today. I appreciate everyone. We had like 20, 30 people watching at one point. I know we at least had 20 something. We might have hit 30. You're welcome, Sarah. We've got a lot. If you're stuck on something, please email me. I'm going to go answer emails now. So go check it out. Answer, email me questions. And I appreciate you guys. We're going to end with some Rick and Morty. Or you know what we got? We got our new rainbow button for imagination. And I got to make sure it's on. So we got our use your imagination. Oh, there we go. It's imagination. I can't get it to go right in my hands because I'm reversed image. Safe is really high for both, with fail being much lower. Yep. And make sure to interpret those confidence rolls to say I am 95% confident the true proportion of machines that are safe is contained in the interval blank to blank. So I am blank percent confident that the true blank is contained in the interval blank to blank. Make sure to make it very clear and use that. This looks skewed, but the third condition passed because the sample size is. Are you talking about condition 2 or 3? I mean, are you talking about problem 2 or 3? Problem number 2 will be success failure, and problem number 3 will be nearly normal. But make sure, as Laura was saying up there earlier, make sure to look at your large enough n part of the nearly normal to see what your sample size is. So I'll kind of talk about that briefly here. So in problem 2 is categorical data. So problem 2, we can find it. Here we go. Problem 2, where's our condition sheet? Where are you, condition sheet? No. Oh, there, we just saw it. I'm hallucinating. There we go. Problem 2 is categorical, so it's success failure. Problem 3 is quantitative, so it's nearly normal. So problem 2 is going to be success failure, and then problem 3 is going to be nearly normal because it's quantitative. So this is engines, whether they're safe or fail, so it's categorical. Success failure is you need at least 10 successes and at least 10 failures. At least 10 successes and at least 10 failures. So you have to see how many machines were safe for new and how many machines failed for new. And they have to see how many machines were safe for current and how many machines were fail for current. It's got it right there. Awesome. Great job, Oliver. Great work. Sports. I think it is time. It is time. So we're going to do our classic Rick and Morty outro right here. It's time for a little Rick and Morty. It's always time for Rick and Morty. So wubba lubba dub dub. See you guys next time. Bye.
Morty, we've got to turn the project in early.